this cast function on the target actor. And if this cast succeeds, then we have an ability system interface. So we can say if ASC interface. And then we have access to the interface by saying ASC interface, and we call that function get ability system component. So that's one way to do it. Now there's another way, and that's by the use of a static function library. You should be familiar with things like gameplay statics and Kismet Math library and static function libraries like that. Well, there's one for GAS as well. It's called U ability system blueprint library, and there's a handy dandy function get ability system component, and it requires an actor. We can pass in target, and what do you think this returns? Well, it returns an ability system component. And of course, up here at the top, writer included that header form. So if you're not using writer, make sure you get that include up there. Now, how does this magic function work? Well, we can go to declaration or use. Usages, and we see that it just calls ability system globals, get ability system component from actor. Let's dive deeper down the rabbit hole, shall we? We'll go to the declaration or usage of this, and if the actor passed in is null, we return null, and look at this. It's casting actor to ability system interface, and if that cast succeeds, it returns the ability system component on that interface. How nice. Well, it also has a Boolean called look for component, and if that ability system interface cast fails, then it uses find component by class. So this function is a little bit better because, well, you might have actors in your world that don't implement the ability system interface. We usually do, right? We mentioned earlier that we implement this interface because it's easy, right? We can always cast to that interface and call get ability system component and get the ability system component. But, well, you know, not everybody follows those conventions and rules of thumb. And so the GAS system has these global libraries that are designed to handle those edge cases. And here's one where the actor may not implement that interface. And if it doesn't, well, this function is designed to look for any component on the actor that has the type ability system component. If it does, it'll find that component and return it. So this is a little more sophisticated than what we were doing, And for that reason, well, maybe you might want to default to using that function instead of this method we were doing, simply casting to the interface and getting the ability system component. It's up to you. If you're in the habit of implementing the interface for all the actors in your game project, maybe that's a policy that your game company will set. You know, your whole dev team may get together, have a meeting and say, we will implement the interface no matter what. Then we can have a meeting and say, we will implement the interface no matter what. Then we can always cast to it and it works. Or you may decide, well, these actors over here aren't going to implement the interface for one reason or another. And in that case, for that reason, you may opt to use the ability system blueprint library function, get ability system component. Either way, you have options. And just so you know, this is blueprint callable, and it's a very handy way to get an ability system component of any actor in blueprint. So there's that. So what we're going to do is use this instead of what we were doing before. So I'm going to replace this line with this one. Where we get an ability system component. I'm going to go ahead and store it in a U ability system component pointer called target ASC. And if you're shaking your head and tisking at me for having ASC in the name, I apologize for that. Feel free to call this target ability system component. And of course, this returns a ability system component, not an Aura ability system component. So I can't have Aura in the type name there. And once we have this target ability system component, we can now apply effects. We can apply this gameplay effect. We have the class, and there are many different options and ways to do things in Gas. And by the end of this course, you'll know just about a dozen ways to do any given thing. The first way that we'll learn how to apply a gameplay effect is as follows. The ability system component, here we have target ASC, which is an ability system component pointer, has a function called apply gameplay effect. And before I finish typing, I want you to notice all of these options. We have apply gameplay effect. This self. We have apply gameplay effect to target. We have apply gameplay effect spec to self. and apply gameplay effect spec to target, and of course, blueprint versions of these. Now, just so we don't get overwhelmed, we're just going to pick one of these. We're going to pick apply gameplay effect spec to self. So let's type that spec to self. And we'll open the parentheses, and we'll see that the first input parameter is a constant reference to a gameplay effect spec. Now, the other input parameter is a F prediction key. Prediction has to do with prediction in a lag compensation sense. We'll get into prediction later. Don't worry about that for now. It's an optional parameter, so we're going to leave it out for now. We just care about the gameplay effect spec. How do we get one of those? If we could just manage to pass one of those in, we can apply a gameplay effect, right? So we want to get an effect spec. Well, we can make one, and the ability system component has the ability to do that. We're just going to use the target's ability system component, because any ability system component can make an effect spec given some gameplay effect class. So we're going to say target ASC, we're going to get that ability system component. I'll go ahead and comment out this line until we're ready. And the ability system component has a function called make outgoing spec. And make outgoing spec takes, well, how about this? A T subclass of U gameplay effect. That's what we have here. T subclass of U gameplay effect called gameplay effect class. We're going to pass that in to satisfy that argument requirement. Now, next is a float called level. You see, gameplay effects can have their own levels. And as our game project gets bigger and more serious, we'll have different levels for everything. But for now, we'll just use 1.f, 1.0f, 1.f, same thing, and f gameplay effect context handle called context. That's the third input parameter that we need. So what exactly is that? Well, a gameplay effect is closely related to something called an effect context. Context meaning, what's the context of the effect? What is the context of the situation? Who's causing the effect? Who's the target of the effect? Is the effect a fire effect, lightning effect? There's really no end to how you can describe a gameplay effect and the context surrounding it. But the gameplay effect context is something that we associate with the gameplay effect, specifically its effect spec, by passing in an effect context, actually an effect context handle. A handle is a lightweight thing that contains the pointer to the context itself. Now, how do we make that context handle? Well, the ability system component has a function for that. It has a function for everything, really. So we're going to comment that line out until we're ready to continue with it, because we need an effect context, right? So we're going to say target ASC, make effect context. This doesn't take any inputs. It's just a function that makes an effect context and returns a handle to that. You see, it returns an F gameplay effect context handle. Now, at this point, we're going to slow down and start taking a look at these types so we don't get confused. We know that this is an F gameplay effect context handle, and we're going to call this effect context handle just so we're not confused. And now it's time to start looking at these types. So I'm going to right click on F gameplay effect context handle, go to declaration or use F gameplay effect context handle. Time to start looking at these types. So I'm going to right click on F gameplay effect context handle, go to declaration or usages, and we see that it's defined here in gameplay effect types.h. And we see that it's a handle that wraps F gameplay effect context or a subclass, allowing it to be polymorphic and replicate properly. So we can subclass the effect context if we want to add things for fire or lightning or poison or really anything we want. It doesn't have to be related to damage or anything like that. The handle is a lightweight wrapper that stores the actual effect context as a pointer. It's called data. See, data is a T-shared pointer of type F gameplay effect context. So data here is the true context. The handle itself is just a wrapper that has a couple of utilities. It has the ability to clear that pointer. We have an isValid function to check if it's valid. We have a way to get any gameplay tags that effect context may have, and we'll learn more about those later. We can add things like instigators, set abilities. It has a bunch of utilities, but really at the heart of this handle is the context itself called data. So make effect context is just a way to create that wrapper that contains an internal gameplay effect context, and we can set things on that context. For example, we can take effect context handle, and we can call add source object. So if we want to know what caused this effect, we can store a source object and just peek this definition, add source object. We see that it takes the data inside and calls add source object. And if we check out the definition of that, we see that now we're inside the effect context struct, F gameplay effect context. And what does this do? Well, it takes that U object and it sets an internal member variable called source object. It uses a weak pointer. And that basically means it won't affect garbage collection. It won't affect reference counting for garbage collection. So the gameplay effect context has the ability to store things related to the context of the gameplay effect. So we'll go ahead and add the source object so that, say, sometime down the line, we need to know what object caused this effect. Well, we can know by checking the source object on the effect context, for instance. So now that we have an effect context, we're going to uncomment the next line where we're calling make outgoing spec, which needs that effect context. We're going to pass it in for the third parameter. And this function requires an F gameplay effect context handle specifically. So we can just pass in the handle like so. Now make outgoing spec returns an F gameplay effect spec handle. Spec returns an F f gameplay effect spec handle. So let's store that in a local f gameplay effect spec handle. And we'll call this effect spec handle. No need for that equal sign there. There we go. So you'll see a lot in gas code. These words like handle will be omitted. For example, we know that make outgoing spec returns a spec handle, right? You'll see oftentimes in gas code that a spec handle will have the name effect spec without the handle on it. So be aware of that if you're looking at other gas code in other projects. You'll see effect spec and you'll hover over it and you'll see, well, it's actually an effect spec handle. That's pretty common to leave off that handle part because, well, it makes the variables longer. But in this case, we're going to try to keep it descriptive of what it is so as to avoid confusion. But just know that you might see a variable called effect spec or just spec that really is an effect spec handle. So look at the type to be sure. Now, these handles are wrappers, right? We've seen that the effect context handle is a wrapper that holds a gameplay effect context. Well, similarly, an effect spec handle is a wrapper that holds an effect spec. We can go to the definition of this and see that it's an effect spec handle. The comment says allows Blueprints to generate a gameplay effect spec once and reference it by handle to apply it multiple times to multiple targets, etc. And notice it has its own data of type gameplay effect spec. It's wrapped in a T-shared pointer, but you get the gist. It has a data member variable. So these wrappers, these handles, have an internal data member that stores the actual struct, in this case, a gameplay effect spec. So we went through all that just to get this effect spec handle, which now has the effect class, a level, and the effect context handle all set for it. Now we can take our target ASC and call apply gameplay effect spec to self, which takes the f gameplay effect spec, but we have an effect spec handle, not an effect spec. This function needs the effect spec, not the handle. So we need to get that data from inside the effect spec handle. And notice that it takes an f gameplay effect spec by const reference, not by pointer, but by const reference. And we know that that data is a pointer inside of our handle. So to get that data, we take our effect spec handle and we access data. Data, as we saw, was a smart pointer. So data itself is also yet another wrapper to get that raw pointer inside of it. We got to call get, right? So right-clicking and going to the declaration of data, we see that it's a T-shared pointer, at least in f gameplay effect spec handle. And to get that raw pointer inside of the T-shared pointer wrapper, we have to use get. Now, that just returns us the raw pointer, but as I said, this function doesn't take a pointer to an f gameplay effect spec. It takes a const reference, so it can't be a pointer. We have to dereference the pointer. So using the asterisk, that's going to get rid of those squiggles. Now we've drilled down to the gameplay effect spec buried down deep inside this gameplay effect spec handle. So it's a little bit of kind of syntax nightmare, but you take the effect spec handle, you get the data, which is a T-shared pointer, storing a f gameplay effect spec pointer in its raw form. You call get to get that raw pointer, and then all of this gets dereferenced into the f gameplay effect spec that apply gameplay effect spec to self craves and desires. And with our semicolon there, we now have a successful call to this function. So as long as our T subclass of is set to some gameplay effect, apply gameplay effect, the target should work. when we pass that in, and we pass in a target that has an ability system component. Now, to kind of safeguard us, we could check the pointer, target ASC, and do nothing if it doesn't have an ability system component. We could do it that way. And think about this. If something overlaps with the volume, it may not have an ability system component. And in that case, well, we don't really want to crash the program or anything. We kind of just want the pickup to do nothing, right? So what I'm going to do is simply check the pointer. We're going to say if we'll just return and do nothing, but the effect itself should not be gameplay effect class, because this aura effect actor is designed to apply an effect. If it doesn't have an effect, we're going to crash intentionally here. Okay, so this is looking pretty good. We have apply effect to target, and we can call this from Blueprint. So since we have our sphere set up in Blueprint, we're going to call this when overlapping. But we also need to create a gameplay effect, and that is something we're going to get into in the next video, and we'll tie this all together and see our effect actor in action. So in the meantime, go ahead and compile your code. Make sure there are no typos. Interface. That way, we can call it from Blueprint whenever we want. I'm going to go ahead and generate the definition. And here's where we want to apply the effect All right, welcome back. Now, we've gone through all this work to apply a gameplay effect to the target ability system component here in apply effect to target. And remember, we made this function in Blueprint callable, apply effect to target. And we did that with the intention of calling this from Blueprint, because we don't have our sphere component here in C++ anymore. We're no longer responding to callbacks to overlap events in C++. We're now handing that over to the design side, to the Blueprint side, right? So what we like to do is go into Blueprint and call this function after creating an actual gameplay effect. And we're going to make one on our Potion blueprint. So I'm going to go ahead and run in debug mode. That way we can catch if anything happens at runtime and get some information about it. So I'm going to go ahead and open the Blueprint editor that I had open, and that was BP help health potion. And in the event graph, I have on component begin overlap for the sphere. And And my blueprint callable function is called apply effect to target. So if I right click and type apply effect to target, then I get that and I can pass in the actor and the gameplay effect class. Now we don't have a gameplay effect class, do we? If I click on health potion self and search for gameplay effect, here it is. It's called instant gameplay effect class. It's set to none. The only option here is the base gameplay effect class, so we need a gameplay effect. And as we learned in the first lecture for this section, we simply subclass the gameplay effect class. We're going to make a blueprint for that. Now, the way we organize our folder, we have a couple of options. We can have our gameplay effect for the potion just right here next to the potion. But if we plan on using the health potion heal gameplay effect elsewhere in our code, we could put it in, say, a ability system folder that has all gas-related stuff in it. But what I'd like to do is here in Blueprints Actor, I'd like to make a new folder called Potion and put BP Health Potion in there. And I'll just make the effect right here. So we can make a gameplay effect by right-clicking and selecting Blueprint class. And under all classes, we can search for gameplay effect. And there are several options, but we're going to choose just gameplay effect. Select that. And we typically prefix these with GE for gameplay effect. Sometimes you'll hear them referred to as GEs. And we're going to call this print. Now, sometimes you'll open it up in the data only view without the event graph, but other times you'll have just the whole details panel showing across the whole screen. It doesn't really matter. The details panel is all that really matters here. So we have a number of settings here, and we're only going to go over a few of them. We just want a simple instant gameplay effect, meaning we want it to be applied once immediately, and that's it, and it's over. So things like period have nothing to do with instant gameplay effects. We see that period has to do with periodic things that happen every so often, right? It has to do with nothing to do, and that's meaning we over here, going across the whole stuff. Now, heal is prefix the gameplay effect, select that. And we typically prefix these with GE for gameplay effect. Sometimes you'll hear them referred to as GEs. And we're going to call this, but we're going to choose just gameplay effect, select that. And we typically prefix and go ahead and open up this blueprint. Now, sometimes you'll open it up in the data only view without the event graph, but other times you'll have just the whole detail panel showing across the whole screen. It doesn't really matter. The details panel is all that really matters here. So we have a number of settings here, and we're only going to go over a few of them. We just want a simple instant gameplay effect, meaning we want it to be applied once immediately, and that's it, and it's over. So things like period have nothing to do with instant gameplay effects. We see that period has to do with periodic things that happen every so often, right? That has to do with gameplay effects that are not instant. So we don't care about those. Stacking type is also not really applicable to instant gameplay effects because they fire off once and they're done. Whereas gameplay effects that have a duration, such as has duration or infinite gameplay effects, those can be ongoing. They'll be applied to the character and continue to be applied until they're removed or they remove themselves. And at that point, when multiples of the same gameplay effect are applied at once, then you need to start thinking about, do they stack? How do they stack? And so on. Now we're going to skip over granted abilities. We're not interested in those yet. Down here under gameplay effect, this is what we're interested in. And here we see duration policy. The default setting is instant. We could set it to infinite. This effect lasts forever. That's what it says anyway. We can remove infinite effects. Spoiler alert there. And it has duration. The duration of this effect will be specified by a magnitude. We want instant, and we want this effect to affect our health. We want to increase the health, right? So we're going to take our modifiers. This is how we change attributes. And modifiers is an array. An effect can affect multiple attributes. And we're going to click plus, and we've added one element to this array. We're going to expand this index 0 element. And here we have some options. Attribute is the attribute we want this effect to change. So I'm going to open the dropdown and look at this. We have some attributes to choose from. Now, these appear in the form of the attribute set class separated by a dot followed by the attribute name itself. Now, yes, there are two here from the ability system component. We're not going to mess with those. For now, we're just interested in our attributes. And look at that. Aura attribute set has 4 attributes and they're here. So we can choose health. And for modifier op, this is the operation for this modifier. We can override, multiply, divide, add. We're interested in adding a value. And for the modifier magnitude, here is where we can specify what we want to add to the health. Now, scalable float allows us to choose a magnitude. For example, we can choose 25 or 10 or -1 or -100. It doesn't matter. And by default, that's all that will happen when we apply this effect. We'll take the health, we'll add a value of 25 to it, and the effect will be done. Now, use curve table has a dropdown with absolutely 0 options here. So that's kind of funny, right? Well, that's because if we wanted to use a table, we'd have to create our own. Don't worry, we will. This is just a way that we can scale that magnitude based on a table that takes this effects level into account. We're just using a level of 1, and we're just hard coding a 25 here. We're keeping it simple from the beginning. And for the rest of this, we have executions. That's some custom, more complicated calculations. That'll be for more complicated types of effects that we'll implement later in the course. Conditional gameplay effects, same thing. And chance to apply to target, well, you can use a curve table for this. You can also put a value here. I want 100% chance to apply this effect. I don't want a chance that it'll do nothing. So I'm going to leave it at 1. And for application requirement, I don't want any requirements. I want this to just be applied. So that's basically all we need for this simple instant effect. We just want the duration policy instant. We want a single modifier that adds to the health attribute a constant value of 25.0. So I'm going to compile and save. And we have our GE potion heal effect. Now back in health potion, I'm going to set that. Now, we made it a variable. I mean, yes, blueprint callable functions can allow us to sort of hard code values in, so I could set it there. But I'm going to be a good blueprint programmer and find what I call this gameplay effect, which was instant gameplay effect. So I'm going to right click in the event graph, search for instant gameplay effect. And of course, I don't get it because I didn't expose it to blueprint. So really quick, we need to do that. I'm going to save all, close out of the editor, and make this instant gameplay effect exposed to blueprint. We need it to be at least blueprint read only. So we'll go ahead and do that and run in debug. Again, at least blueprint read only. So we'll go ahead and do that and run and debug again. I almost always do that. I rarely give variables blueprint read only by default. I always get to the point where I need to access them in blueprint, and then I go and add that specifier. And that way I'm taking the approach of underexposing rather than overexposing, right? So now that I've exposed it, we can search for instant gameplay effect and get that and plug it in. To our blueprint callable function, apply effect to target. It just needs a target, and when something overlaps, we're going to take the other actor and pass it in as the target and hook that up, and now we have a blueprint for an actor that will apply an effect. Now let's just say we want to destroy the actor. We'll just call destroy actor here, because why not? But later we'll make that a parameter that we can set so that this can be a very versatile class that doesn't have a self-destruction mandatory quality or anything like that. Now, by default, blueprint callable functions get that target self. So target here might not be the best choice of name. Since we have two targets, that might be ambiguous a little bit. So what we'll do is we'll go ahead and close the editor and rename this. So I'll go ahead and rename it to target actor. That way we know the difference here. And I'll go ahead and run in debug mode again. And I'll go ahead and open these blueprint editors. And now this is called target actor and not target. I can simply alt click that and get rid of it. And now other actor can go into target actor. We can compile and that works. So now we need to make sure our instant gameplay effect class is set. We'll go to that. We have GE potion heal. Looks good. And we can test this out. So we can drag in one of these healing potions and press play, and I can show debug ability system. I see that I have 50 health, and as soon as I pick it up, there we go. Go up to 75, the gameplay effect has worked successfully. And we can go into net mode. Let's play as a listen server and change the number of players to 2 and press play. Now I have the client here in the small window, and we see that it works there. Play. Now as a listen server and 95, as soon as I bug ability healing potion, and we can test this out. We have GE instant, and that works. Now other actor can go into target act. We need to make sure our instant gameplay effect looks good. Potions and and press play, and I can show debug ability system. I see that I have 50 health, and as soon as I pick it up, we go up to 75. The gameplay effect has worked successfully. And we can go into net mode. Let's play as a listen server and change the number of players to 2 and press play. Now I have the client here in the small window, and we see that it works there as well. So our gameplay effect is working. Excellent. Okay, so now our effect actor is a little bit more versatile, and this is really cool because if we wanted to, we could make a BP mana potion that will increase our mana as well. And we have this nice apply effect to target. We can choose to destroy the actor if we want to, and all we need to do is swap out that instant gameplay effect class, and things would be pretty easy. Now, it would be a red potion bottle, but if we browse to the asset here for SM potion bottle and open it, we see that it's using 3 materials, one of which is MI red liquid. It's a material instance. In fact, you didn't have to browse to the mesh to do that. You can just see it here in the blueprint. If you browse to MI red liquid, well, look at this. We have MI blue liquid. And if you were to, say, swap them out by choosing blue liquid, you can change it and it looks suddenly like a mana potion. I'm going to change that back, but showing you that because your quest is to make a mana potion. Good times. Make the configure OS, make a folder. And go to blueprint class, search for gameplay effect, and choose that. And we'll call this GE play. I'm going to right click our mana potion here, but blueprint, and we'll open it up. GE underscore potion mana. and we'll effect to be instant. And the I'd like to add a effect. We're going to go ahead and choose that. And with static mesh, potion mesh, to come back in a blue. I see my instant gameplay effect class. Now, let that one, this one, like a blue mana potion. Now, I can set that to GE potion mana. And I want to apply that when something over. I can set that in self, selecting that. I see my instant gameplay effect class. I can set that to GE potion mana. And I want to apply, I'm going to choose you. Hey, I want to do a box collision instead. So why not? I'll make it a box, right? Do a box collision instead by moving this step to the blueprint side. Let's say I want to do a box collision instead. So why not? I'll make it a box, right? And go into event graph with box selected. I can choose to get that on component begin overlap. And see, now I don't have to go class, call my apply and plug instant to destroy. I think that way with target, because this can cause it to, if I only want the main character to be able to, just in case we'll be there. As to the asset, I guess I need to drag a potion into the world. Listen server doesn't matter. I'm not gonna, I can show debug and see my mana, clamping it. We'll learn how to do that. 80, so we know it's working. My mana at 50, now it's at 80, so we know it's working. We're not really clamping it. We'll learn how to do that soon enough. But just to get that cool feeling that you get when you see that health globe or mana globe change, I'm going to go into my attribute set and start my mana off at a lower value. So closing, private, and public. I'm going to go into ability system attribute set. And right here, I'm going to init my mana to 10. We really need mana. So let's run a debug mode. Need a potion. There it goes. And we have working potions and are awesome. And we're going to see how awesome ++ class things over to the blueprints. Developers will say that they tried to doing so. And so it's important to kind of welcome back. Now, we know how to create an instant gameplay effect, and applying that gameplay effect is relatively simple. And we applied it using a blueprint callable function, which we're calling here in response to an overlap. Now, before we move on to different duration types for gameplay effects, we should visit how to apply these gameplay effects directly here in Blueprint without having to call a blueprint callable C++ function. And our C++ function here in Aura Actor involves getting the ability system component for the target simply so we can use it to make an effect context and apply a gameplay effect after making an effect spec. This is actually quite simple to do here in Blueprint as well. We can take our other actor and we can call get ability system component. And if we hover over this, we see target is ability system blueprint library. And that's the function we ended up calling here, ability system blueprint library, get ability system component, which takes a target actor. Here we have the input actor and the return value is the ability system component. Now, once we've gotten that ability system component, we take it and make an effect context with make effect context. We can do that here in Blueprint. We can drag off of the return value and type make effect context. And this function returns a gameplay effect context handle structure, just like make effect context here in C++ returns a gameplay effect context handle struct. Same thing. Now here in C++, we're calling this add source object function. Now if we go to the definition of this, we'll see here that it exists in gameplay effect types, and it's right here inside of, scrolling up, our fGameplay effect context handle. But we see that this function is not blueprint callable. So we can't call this from blueprint. We also have get source object, which is also not blueprint callable. But here in blueprint, if we type in source object, we see that we have a get source object. So how can we call this in blueprint if it's not blueprint callable? Well, this is not a function on this struct. It's a function on ability system blueprint library. So these static libraries are a great way to expose to blueprint certain things that you can only do in C++. And later on in the course, we'll be making our own blueprint library that we can use to expose certain utilities to the blueprint side like this. So while we can't call add source object, we could make a static function library, a blueprint library of our own, and create a static function that could take in an effect context and call a function such as add source object, for example. So that's one of the limitations of doing this from blueprint. But closing gameplay effect types and going back into or effect actor, the next thing we did was we made an outgoing spec, this gameplay effect spec handle. This is a function on the ability system component. So from here in blueprint, we could drag off and type make outgoing spec. And notice that make outgoing spec requires a gameplay effect class, which we have one here. We have instant gameplay effect class. If I duplicate that node and plug it in, that will satisfy it. We can also set the level. In C++, we set it to 1, and it takes a gameplay effect context handle structure. That's what make effect context returns. So we could simply plug that straight in there, and we now have an outgoing spec. Now, the last thing we did here in C++ was call apply gameplay effect spec to self on the ability system component. Here in blueprint, we can take our ability system component and call apply gameplay effect spec to self. We see that there are other options here as well, but if we choose apply gameplay effect spec, not effect, but effect spec to self, then we see that we can plug in a spec handle. That's the return value for make outgoing spec. So as you can see, this looks a little bit cleaner in blueprint, as here in C++, we had to get the effect spec handle and get the data, which is a pointer wrapper. We had to get the raw pointer and dereference it in order to pass in that object. Here in blueprint, we don't have to do any of that. We just call a handful of functions that are exposed to blueprint, and it's a little bit easier, a little quicker to do, but you can do it either way. And we've seen that on the C++ side, we do have more options, as not everything in C++ is exposed to blueprint. And another benefit is we did all this work in C++ right here in our blueprint callable function. So the end result is that our blueprint is cleaner, as we only have a single node. And as things get more complex, we'll be able to implement those in C++. But really, using one versus the other is really not going to result in, say, a significant performance difference, at least in this case, as we're doing simple things here. But to make sure that this works, we could bypass our blueprint callable node, and we can simply call apply gameplay effect spec to self and simply destroy the actor after that, like so. And if we wanted to make sure that this only works for an actor that has an ability system component here, we can add an is valid to the ability system component. We can say is valid here, use the one with the question mark, and run it through the is valid node first, like so. And we can tidy this up just a little bit. This does get a little bit messy in blueprint. Another reason to opt for the C++ option, as blueprints can get a bit out of hand. And ideally, this could be collapsed into a function of its own and cleaned up even further. But let's just make sure that we can prove to ourselves that the blueprint option works. Let's go and pick up the health potion. That's the one that we changed. And we see that it works. And we're not using the C potion. That's the one that we changed. Now we're using the blueprint option. options. So 2 options for for you, and I'll just leave those nodes there for now, but we're using our C++ function. Okay, great. Just moving that out of the way. Now for the topic of this lecture, and I'll just vocalize it. I hooked up destroy actor. And everything's back to how it was there. Now, the topic for this lecture is the different types of duration policies for our gameplay effects. We have a GE Potion Heal, which is an instant gameplay effect. Our Potion Mana is also an instant gameplay effect. But instant is just one of 3 choices. We also have infinite and has duration. In this video, I'd like to discuss has duration and see how the has duration type works. So to showcase the has duration gameplay effect, I'd like to make a new one. I'm going to right click here and create a new blueprint class. I'm going to search for gameplay effect, choose that class, and call this one GE underscore. And this will be the duration based heal. So I think I'd like to use something other than a health potion. The assets folder in this startup project has a crystal. So I'm going to say crystal heal, and we can make maybe a healing crystal, for example. So I'm going to open up crystal heal, and here in the details panel, I'm going to scroll down to the duration policy and change it to has duration. Now that it's has duration, we need to specify the duration magnitude. Essentially, how many seconds is this effect going to be applied before it removes itself? So for the duration magnitude, we have scalable float, attribute based, custom calculation class, and set by caller. So far, we only have experience with scalable floats, which as we know, we can hard code a value in, and we can also scale it by a table. Now we haven't created a table yet. Don't worry, we'll get to all these features. We're going to cover them all, but I'm going to set a scalable float magnitude of 2. And this is in seconds. So this effect will be applied for 2 seconds, after which it will remove itself. And if we have any modifiers here, those modifiers will be undone. So for example, if I want to modify one of my attributes, I can add a modifier with the plus icon, and I can select the attribute. Let's say I want to select max health. And for max health, I'd like to add to it. And for the modifier magnitude, expanding that, I'm going to set the scalable float magnitude to 100. So in other words, the max health will be added to by 100. Now, the max health is already starting at 100, which means it will be now 200 for 2 seconds. And the result of that is we should see the health globe actually appear to go down because the amount of health, the current health value health, is going to be the same, but max health will be larger, which means the percentage of health will be the same value divided by an even larger value for max health. So we should actually see that health globe go down. It'll look like you have less health. You really have the same amount of health, but the max health has changed. So we have this crystal heal, right? And we want to apply this duration-based effect. And we can easily do that by creating a new blueprint based on our aura effect actor and setting its effect, but we called our effect instant gameplay effect class. We should add a new variable for a gameplay effect that has a duration. So what I'm going to do is I'm going to save all, I'm going to close the editor, and we're going to add one more variable to aura effect actor. We'll go ahead and rearrange these here. I'm going to close out of the files I'm not using. And just under instant gameplay effect class, I'm going to add another tsub class of holding a gameplay effect. And this one will be called duration gameplay effect class. So we'll have a different variable here. So what we can do is now we can make a blueprint for the health crystal that actually applies the duration gameplay effect and not the instant gameplay effect. So that's what we'd like to do. And that's going to be your quest. I'd like you to create the health crystal. You're going to and then create it, make that effect class. So I can make it. I'm going to on aura effect potion folder, potion crisp mesh, and some kind of overlap volume. So I'll do that first. I'll select the root component, create the static mesh, simply call this mesh, and I'll search. And it's quite large. So I'm going to scale it on down by about 0.2 in each dimension. And I'll add a collision volume. And for this one, since I can, why not? I'll go ahead and add a capsule aimed without size. I could and move it more precisely and go to right and move it more precisely. All right, looking good. I'm going to make sure my crystal mesh has no collision. Some of those things you typically do for things like these pickups. I'm going to go to my capsule collision settings here, and it's set to overlap all dynamic. I'll just leave it at that. That's fine. It's set to generate overlap events. Perfect. And I'll go to health crystal self and search generate overlap events. Perfect. Dynamic. I'll just leave it collision do for things like these pickups. I'm going to go to my capsule. We typically do for things like these. Pickups. I'm going to go to my capsule collision settings here, and it's set to overlap all dynamic. And I'll go to health crystal self and search for duration, and here's duration gameplay effect class. I'll set and take my capsule, and I can either use my blueprint call begin overlap to apply the effect and drag. What we should see, because our health will be the same value, but our max health will be twice as large, this should go down. And I can even show debug. Remember to click in the viewport before hitting tilde key. Show debug, ability system. And I see health is 50, max health is 100. Let's pick up that healing crystal. And now we see max health is 200. Oh, but now it's back to 100. Why? Because this is a duration-based gameplay effect, and we set the duration to 2 seconds. Let's see that again, because 2 seconds isn't a long time. Here's the health. Goes down, but 2 seconds later, it comes back up. Now, this is extremely useful because without that built-in capability of gameplay effects, we'd have to create our own timers and create callbacks for when the timers finish, and it's all a lot more work, whereas all we needed to do was make a gameplay effect and just set its duration and the duration magnitude, and it was quite easy. Now, setting our max health to what it was plus 100 for 2 seconds and then setting it back to what it was before, that's kind of silly. It's not really a gameplay mechanic that you would think up and decide to implement in a game. This was just for demonstrating how a duration-based gameplay effect works. But in the videos to come, we're going to see how we can have a gameplay effect apply changes periodically. In other words, every so often, apply some kind of change, such as healing over time and things like that. And those are the type of things that you would see in a game. So great job this video. We learned about duration-based gameplay. So we'll do that in the videos to come. Great. See you soon. Welcome. Now we know how to apply instant gameplay effects. And we also know how to set a duration for gameplay effects. And we saw that at the end of that duration period, the effect was removed or undone. Now we can also have effects that execute some sort of change periodically. But before we get into those, we need to have a bit of a deeper understanding of the difference between these duration policies and how they affect the attribute. You see, we know that the attribute has a base value and a current value. And we've already mentioned that temporary effects affect the current value. And when those effects are removed, that current value has that effect undone, and the current value goes back down to the base value. Now, we've seen that instant effects seem to be permanent, and that's because instant effects affect the base value with a permanent change. So when we apply an instant effect, we're not applying that change to the current value because we don't plan on undoing it later. Now, this is different than how duration and infinite effects work. We haven't created any infinite effects yet. We will. But they work similar to the duration infinite effect in that they cause changes to the current value, which can be undone if and when the effect is removed. Now, duration-based effects remove themselves. We set the duration, say 2 seconds, and after 2 seconds, the effect is removed, which means any changes to attributes are then undone. This is why the change is applied to the current value. Infinite effects behave similarly. The only difference is they don't remove themselves. If you want to remove them, you have to do so manually. Now, duration and infinite effects can be converted into periodic effects, which means that they execute some kind of change to an attribute periodically, every so often, as long as that effect is currently applied. So periodic gameplay effects are a special flavor of duration and infinite. But the periodic changes that they execute are treated like instant gameplay effects, in that they change the base value permanently. They're not something that you undo. If a duration or infinite gameplay effect that's set to be periodic is removed, all of those changes that occur every period are permanent. They don't get undone when the effect is removed. So that's how periodic works. And we can convert any duration or infinite gameplay effect into periodic by simply changing its period to a non-zero value. And that's what we're going to do to our health crystal now. So I'm back here in the editor, and I have my GE crystal heal. Now this is a gameplay effect with its duration policy set to has duration. And this just means that the effect is applied, and then it removes itself after an duration crystal heal. Now this is a gameplay effect with its duration policy set to has duration. And this just means that the effect is applied, and then it removes itself after an amount of time, and that's scalable float magnitude, which we set to 2 seconds. Now, the modifier is applied as soon as this effect is applied. So we chose the attribute max health, we chose the operation to be add, and the magnitude to be 100. So max health will have 100 added to it, but because this has a duration, that 100 is removed at the end of that duration. Now we can change this to a periodic gameplay effect by scrolling all the way up to the top, and under period we have a period property and it's set to 0. If this is set to 0, this is a non-periodic effect, and period doesn't apply. But if we set this to a non-zero, non-negative value, such as, say, 1, then this effect will be applied every 1 second. Now, execute periodic effects on application is a Boolean we can have checked or unchecked. If it's true, then as soon as we apply the effect, then the modifiers will be applied instantly as soon as the effect is applied. But if you uncheck this, then we have to wait 1 period before we get that first application of the periodic effect. So nothing would happen for a whole second. And then the modifier would be applied. I'm going to leave it checked. And because we have a period of 1 second now, our modifier will be applied as soon as we apply the effect, and then again after a second, and then again after another second, because we have a total duration of 2 seconds. Now let's change this attribute from max health to just health. And instead of adding 100, I'd like to add, say, 10. And we can just check out how this works. I'm going to compile, press play, and enter the show debug command so we can see that our health is 50. And I'm going to go ahead and pick up our crystal and see what happens. We see 60, 70, 80, and it stops. So every second we get 10 added to our health. Pretty nice. You can adjust these parameters to your heart's content. We could change the magnitude to 1, and we can change our period. Instead of 1 second, we can choose 0.1. So a tenth of a second. In other words, the effect will be applied 10 times per second, and each time we'll add 1 to the health. That gives us a bit of a more rapid health increase. If I keep an eye on the health globe and pick up the crystal, I see that it's growing steadily. Now, you might be tempted to really crank this by setting the period to, say, 0.01, right? 100 times per second. And at each period, we can increase the health by 0.1, and then we get a much smoother increase, right? Let's take a look at that. There we go. That's much smoother, right? But keep in mind that gameplay effects are predicted, and they register these changes with the ability system each time. So it's not really just a trivial setting of a variable, but there are potentially other things that happen as a result of application of gameplay effects. So while you can apply effects this rapidly, really, you're going to want to achieve that smoothness in potentially other ways. For example, if I set this to increase, say, only 10 times per second or once every quarter second, we can interpolate and show the health changing in a smooth manner with tricks on the widgets, rather than just forcing this effect to have its modifiers applied so rapidly. So what I'm going to do is set this to 0.1 and set the modifier to 1. I think that's a pretty decent balance. And that way, as we pick up the health crystal, we get 10 times per second, 1 health added every single period. And that seems pretty decent. So now we know how to apply periodic effects by simply changing the period to a non-zero value. Now notice if I change the duration policy back to instant, I can scroll up and notice period doesn't have the ability to set the period. So period only becomes an option when you change it to has duration or infinite. As soon as you change that, then you can go back up and see the period. And notice it remembered my 0.1 seconds. Now, let's go back to execute periodic effect on application again. With this checked, which it's been checked the whole time, I'm going to show debug, and we see that our health is 50. I'm going to pick up the crystal, and notice it goes all the way up to 71. We're applying our effect 10 times per second for 2 whole seconds. So we're adding 1 to our health each period, and there are 10 periods per second. But we started with 50, and we ended up with 71. It seems like there's an extra 1 there, right? And that's because we applied the modifier on execution. That's because of the setting here, execute periodic effect on application. That's application of the gameplay effect itself. Now, if we uncheck that, then we'll have to wait a whole 1/10 of a second before we see that modifier applied. So with it unchecked now, I'm going to show debug and pick up the crystal, and we see that it goes all the way up to 70, but not 71. So that's the difference there with this checkbox. So it depends on if you want that modifier applied instantly when the gameplay effect is applied, or do you want to wait one full period. Now, periodic inhibition policy has to do with gameplay effects being inhibited. You see, gas is very versatile, and we use gameplay tags to block things or cancel things. Gameplay effects can be blocked or inhibited based on tags that a specific ability system component may have. And we'll learn more about that when we get into gameplay tags very shortly. But once we get into them, we'll see that the inhibition policy allows us to choose what to do when our gameplay effect becomes inhibited. For now, that doesn't apply to us. And one last thing before we move on to your quest for the video is notice that we have a stacking type, and stacking allows us to choose what happens when we have multiple gameplay effects of the same kind applied at the same time. And we'll get into those very shortly as well. We won't get into them in this video. For this video, it's enough that we know that we can now apply periodic gameplay effects, and our health crystal has now a healing over time quality, which is kind of nice. And it'd be nice if we had something similar for mana. And that's going to be your quest for this video. I'd like you to make crystals or periodic mana playtest. So pause the video and make your periodic mana pickup now. Help change my mana, right? Since I need a gameplay effect, that's going to change my mana. right? And really, I can use my GE Crystal Heal as a bit of a template to base my mana effect on. So I'm going to make a new blueprint class. It's going to be based on gameplay effect. There we go. And I'll call this GE Unbelievable Heal. This point because I to have ahead and change it to application layer. And change the attribute add one magnet mana based. I'll select that. BP is sure putting it like the roots of work, isn't it? Let's get this effect active. And we have the help on and kind of as well. What I think I'll do is use this SM shard debris. Which is a bit, and I always go to the end, apply effect, this that we need to add, and hook up other actor to the end. And press play. Crystal it all the way up, which is exciting. 3/10 of a second. Definitely make the time. Don't worry. Us instant changes to duration based, which is exciting. So excellent job. And we're going to continue with our study of gameplay effects in the videos to come. I'll see you soon. Welcome back. Now let's take a look at one of our gameplay effects. I have Crystal Mana open here, and I'm going to scroll down, and because this gameplay effect has duration, we have the ability to configure its stacking options. Notice we have a stacking section, and we have stacking type. And stacking type can be set to none, or aggregate by source, or aggregate by target. Now, it's set to none, and I want to see what happens when we pick up 2 of these, or maybe 3 or 4. So I'm going to take this mana crystal, or maybe 3 or 4, and I want to see what, or aggregate by target, be set to none, or aggregate by source, or aggregate by target. Now, it's set to none, and I want to see what happens when we pick up 2 of these, or maybe 3 or 4. So I'm going to take this mana crystal and duplicate it a few times, and I'll have these sort of all next to each other so we can pick them all up very rapidly. And let's see what happens with none as the stacking type. I'm going to pick all 3 up, and look at that, our mana goes up. And in fact, let's look at the numerical value using show debug. Our mana is set to 10, and if I pick up all 3 of them, look at that, it's going up really rapidly. Now that seems like stacking, doesn't it? But that's not what stacking really is. is, without any stacking, we just apply the effect 3 times. Each one has its own duration, and they're all sort of being applied at the same time, and we end up getting 3 times as much mana as if we were to pick up just a single crystal, right? So that's the behavior without stacking. So what behavior do we get with stacking? Well, if we do have stacking and we choose one of these options, we can choose exactly what type of behavior we see. For example, let's say we wanted to pick up 1 crystal, and that crystal has a duration of 2 seconds. Well, what if during that 2 seconds we pick up another crystal? What behavior would we want to see? We don't want our mana increasing twice as fast. Maybe we want to still just increase mana at the same rate, but we want to refresh that duration. So say we pick up the first crystal, and 1 second in we pick up the second crystal. Maybe we just want the duration refreshed, so we get our mana increased for another 2 seconds. It's things like that our stacking parameters allow us to configure. So the first 2 things we should talk about are these options for the stacking type: aggregate by source and aggregate by target. How do these work? So the first stacking type option, aside from none, is aggregate by source. Let's see how this works. Let's say we set our stack limit count to 2. Well, aggregate by source means that stack limit count is enforced per source. So if we have 1 source and it applies a gameplay effect to the target, we count that as 1 stack of the gameplay effect, and it's aggregated on the source. So the source now has 1 stack count for this gameplay effect applied to the target. Now the same source applies that same gameplay effect again, right? And we count this as the second stack, and that's aggregated by the source. Now at this point, we have 2 stacks of the gameplay effect, and that's the limit. We set our stack limit count for this effect to 2. So if the same source applies the same effect again, this would be the 3rd stack, but that exceeds the limit, so this effect can't be applied. Now, we're aggregating by source, which means each source keeps a count of the stacks of this particular effect caused by the source. So say we get another source in the game that applies the same gameplay effect. Well, we're aggregating our stacks by source. So for this source, this is only the 1st stack, and so we aggregate that stack by that specific source. So now the target has 2 stacks of this effect applied from the 1st source and 1 stack applied from the 3rd. Now that may seem to exceed the stack limit count, but we're aggregating by source. So we can have a maximum of 2 stacks per source applied to the target. Now let's compare this to the other option, aggregate by target, with a 2 count, but word. Now that may first, now the target has 2 stacks of this effect applied from the 1st source and 1 stack applied from the 3rd. Now that may seem to exceed the stack limit count, but we're aggregating by source. So we can have a maximum of 2 stacks per source applied to the target. Now let's compare this to the other option, aggregate by target. Before we were aggregating by source, now we're aggregating by target. So say we have a source, it applies the gameplay effect. This counts as a single stack. And this stack is aggregated by the target this time instead of the source. Now that same source applies the effect again. This counts as the second stack, and that's added to the stack count, which is aggregated by the target. Now the same source can attempt to apply another stack, that would be the 3rd one, but of that exceeds the stack limit count, right? So as we expect, that stack cannot be applied. But along comes another source attempting to apply this effect, and if we were aggregating by source, this source hasn't applied any stacks yet, but we're aggregating by target, and the target already has 2 stacks applied. So for this new source attempting to apply this effect, this would be the 3rd stack on the target. And the stack limit count is 2, this would exceed that. So this effect cannot be applied. So that's the difference between aggregating by source and by target. By source means there's a limit per source, but by target means there's a limit per target. So in our case, let's say we choose aggregate by source and we set a stack limit count of 2. Now the duration I'd like to set to 1 second to make our math simple here, and the period is going to be 0.1, and I'm going to uncheck execute periodic effect on application. Now this means that from check execute and to 1 second. Second to make our, now the duration I'd like to set to 1 second to make our math simple here, and the period is going to be 0.1, and I'm going to uncheck execute periodic effect on application. Now this means that for 1 second we'll execute our modifiers 10 times, and because we're adding 1 to our mana, we should see a total of 10 added to our mana over the space of a second per mana crystal, right? That makes sense? So let's duplicate one of the crystals and move it over here, press play, show debug ability system, and we see that our mana is 10. And if I pick up a single health crystal, I should see it go up to 20 within the space of a second. Makes sense. Okay, now we set our stacking type to aggregate by source with a stack limit count of 2. Well, what do we mean by source? Source is referring to actually an ability system component that's causing this. So we're causing this effect by actors. So in our case, it doesn't matter if we choose source or target, we're going to get a stack limit of 2 enforced. So we should only see our mana go up by 20 total. So we have 10. If we pick up all 3, we go up to 30, which is 20 more than we had before. So once we start having ability system components as the source, we should start being able to test that ability system components as the source. Course, we should start being able to test that out. Now we have a stack duration refresh policy, and it says policy for how the effect duration should be refreshed while stacking, and it's set to refresh on successful application. If we choose never refresh, then even though we're adding stacks, that duration of 1 second is what prevails. So if we set this to never refresh, and we go on to pick up some mana crystals, I'm going to show debug. We have a mana of 10. I'm going to pick one up and then pick up another. Notice we didn't get all the way up to 30 because that full second had elapsed before we reached 30. So it doesn't matter how many stacks we have. This effect will expire at the end of a second no matter what. But with refresh on successful application, each time we stack another one on, it resets the duration and you get an additional second. Now we have a stack period reset policy, and this is similar to the duration refresh policy, only it's for the period itself. So if you're waiting for the next periodic change to an attribute, when we stack a new stack of this effect, reset on successful application means reset that period and start waiting for another full period. Otherwise, never reset means, well, we won't reset that period. And expiration policy is set to clear entire stack, which means as soon as this effect expires, all of the stacks are cleared. But you can choose to set this to remove single stack and refresh duration, which means that as the duration finishes, we remove a single stack and then the duration starts over again. So you can have 2 of these effects stacked on, and when the duration expires, the stack count goes down to 1, and then the duration count starts over again. So as you can see, we have a lot of options when it comes to stacking, and it really just depends on how you want these things to stack in your game. And throughout the project, we'll be creating lots of effects and choosing how they can stack. For now, for the mana crystal, I'd like to leave it at aggregate by target with a stack limit count of 2. I'd like to refresh the duration on successful application. I'd like to reset the period on successful application. And as soon as a stack expires, I'd like to clear the whole stack, and the duration can be left at 1. And the stack expiration policy, I'm going to set to remove single stack and refresh duration. That way, as we pick up more and more crystals, then we extend the duration and we can potentially gain more mana. So if I spread these out, we can kind of see the result of this combination of parameters. So I'm going to press play. I'm going to show debug, and I have 10 mana. If I pick up one, I just get 10 more mana. If I pick up another one and then another one, I got 20 more. And that's because I refreshed that duration when I got a new stack. But if I start off with 10 and I pick up all 4 of these, notice that I only go up to 56, and that's because I'm picking them up one after the other, and each time I pick it up, I reset that duration. And notice that no matter how many stacks I have, I'm always just gaining 1 mana every 10th of a second. Whereas if we didn't stack it all, if I set this back to none, then picking up a whole bunch of these results in a very fast increase in mana. And setting it back to, say, aggregate by target with a stack limit count of 1, for example, then we can continue prolonging the stack duration, but always get the same rate of increase of mana. So let's pick up all of these, and we'll see that we increase that duration, but we're only ever getting 1 mana 10 times a second because we're limiting to 1 stack. So picking up a crystal before the previous stack expired simply resets the duration. So I know it's kind of a lot to take in, but we have a lot of options here, and we'll see how they can be combined and set up throughout the course. Now, the last of the stack expiration policy is refresh duration, which means that when this stack expires, refresh the duration, even if it's the one and only stack. This essentially makes the effect infinite in duration because it keeps refreshing. So the comment says this can be used to manually handle stack decrements via on stack count change callback. So there's ways to respond to when the stack count changes, and we'll get to that. But if I set this to refresh duration, watch what happens if I pick up just a single crystal. We see that it keeps going and it never stops because each time the stack expires, we refresh the duration. So that's a way to get a sort of infinite duration periodic effect. I'm going to go ahead and leave this at clear entire stack. That way, as we can pick up multiple ones, we'll clear the stack completely as soon as that duration runs out. And before we wrap up, why don't we just go to the Crystal Heal gameplay effect and set its stacking type. I'm going to set it to aggregate by target, set a stack limit count of 1, and just like Crystal Mana, we'll leave it at refresh on successful application and reset on successful application. And just like Crystal Mana, we'll leave it at clear entire stack as well. And that way we've got a little bit of throttling entire by target gameplay effect. And the stack, as we keep this at duration, we refresh it, keeps going and it never just because sort of in infinite duration periodic effect. I'm going to go ahead and leave this at clear entire stack. That way, as we can pick up multiple ones, we'll clear the stack completely as soon as that duration runs out. And before we wrap up, why don't we just go to the Crystal Heal gameplay effect and set its stacking type. I'm going to set it to aggregate by target, set a stack limit count of 1, and just like Crystal Mana, we'll leave it at refresh on successful application and reset on successful application. And just like Crystal Mana, we'll leave it at clear entire stack as well. And that way we've got a little bit of throttling if we pick up too many at the same time. So great job. We now know about stacking, and I'll see you in the next video. Blueprint callable. And I'll go ahead. Entire stack. Welcome. In this video, we're going to make an infinite gameplay effect, which means our effect actor should have an infinite gameplay effect T subclass of. So we're going to go ahead and add one. I just copied duration gameplay effect class, and I'm going to name this one infinite gameplay effect class. And with that, I'm going to hit debug, compile, and launch. And here in the editor, I'd like to make a new gameplay effect. I'm going to go to Blueprints, Actor, Potion, and it's time, I think, to organize these a bit. I'd like to have a folder for the health and mana crystals. So here in Actor, I'm going to make a new folder called Crystal. And from Potion, I'm going to move the Health Crystal, the Mana Crystal, and Crystal Heal, and Crystal Mana. With all of these selected, I just held Control and left click. Clicked on them. I'm going to move them over to the Crystal. And here in Actor, I'm going to have a new type. So I'm going to create a new folder. And for this one, I'm going to call it Areas, or just Area, rather. And you'll see UI, I'd like to make something that spans across an area. So I'm going to right-click and make a new blueprint class. I'm going to make an aura effect actor, and for this, I'm going to search. For box, get a box collision there. And in addition to this, I'd like to have some fire. So I'm going to add a Niagara part and get a box collision there, component. So I'm going to search for box, get a box collision there. And in addition to this, I'd like get a box collision there. And in addition to this, I'd like to have some fire. So I'm going to add a Niagara particle system component and call this fire effect. And fire effect gets a Niagara system asset. I'm going to choose in S. Fire. So here we have a fire Niagara system and a box that will occupy an area. Now, this is kind of cool. If I drag one of these out into the world, my BP fire area, we see that it has fire. And I'm going to go ahead and move it a little closer to my player start. So we have a fire area here. And for the fire area, I'd like to apply an infinite gameplay effect when the character is overlapping with it. And an infinite gameplay effect is never removed, at least until you remove it manually. So that's kind of what I want to do for the fire. So in order to remove an infinite effect, that's going to require some thought. But for now, I'd like to just apply the infinite effect and see what happens. So here in my area folder, I have my fire area. I'm going to right-click and make a new blueprint class based on gameplay effect and call this GE underscore fire area and open fire area. And this will be an infinite gameplay effect. So duration policy will be infinite and infinite gameplay effect. So duration policy will be infinite. And we now need to decide what to do when we apply this effect. Well, I'd like this to be periodic, so I'm going to go up to the period, and I'll give this a period of 1 second. So every second, we'll be applying any modifiers, and speaking of modifiers, we'll add one, and the modifier is going to affect the health attribute. It's going to use an additive operator, and what are we going to add? We're going to add a negative value. So we can subtract from the health. I'm going to subtract 5 from the health every second. So we have the fire area. Let's compile and save. And here in BP Fire Area, I'm going to select BP Fire Area self. Here's my infinite gameplay effect class. I'm going to choose GE. Fire area. And now we need to apply it. So here in the blueprint event graph, I'm going to get my box, right click on component, begin overlap. Box, right click on component, begin overlap. And I'm going to simply apply my plugging in the other actor for target actor. And I'm going to get my infinite gameplay effect class and hook that in. And I'm not going to destroy the actor. So on overlap, we apply an infinite gameplay effect. So what happens? Let's go and find out if we overlap with this area. I'm going to press play, and I'm going to overlap with the fire, and there's my health going down. Every second, it's going down. Now, here's the problem. If I leave the area, well, the effect is still applied, and if I show debug, we see health going down into the negatives. It's never going to stop. So if we do apply an infinite gameplay effect, it's up to us to remove that effect. And so in this video, we're going to learn how we can do that, and we'll handle this on the C++ side of things, as this is one of those things that I feel makes more sense to handle in C++. So what I'm going to do is I'm going to close the editor, save all, and let's think about how we're going to handle these gameplay effects in our effect actor, depending on which ones are set here. Now we need to think about how we'd like to handle applying our different types of effects. Because we have an instant effect, we have a duration effect, and we have an infinite gameplay effect, we have to decide how the aura effect actor is going to apply and or remove these effects. And I'd like to be able to change how the actor applies the effects from the blueprint. I want this to be nice and flexible and configurable. So what I'd like to create is a policy, an enum, for the effect application and the effect removal. So we'll have an effect application policy, essentially a setting that we can set that determines whether we apply any of these effects on overlap or on end overlap, and so on. So let's create an enum up here at the top. We're going to make a scoped enum. We're going to say enum class e, and this is going to be our effect application policy. So we're going to say e effect application policy. In other words, how are we going to apply the effect? And it's going to be a uenum. We're going to make it blueprint type and constants for our policy. Policy will be apply effect or just apply on overlap. We can have apply on end overlap. We can have do not apply. And if we create a variable of this type for each of these, we can set it in the blueprint. For example, we can have an E effect application policy for the instant effect. So we can call this instant effect application policy. And we can make this edit anywhere. So I'm going to give it a U property. Make it edit anywhere. And it can be blueprint read-only category applied effects. So really, I'll just copy this U property from up there. So we have one for the instant effect. We can have one for the duration effect as well. So I'll copy and paste it here. And then we can also have, now in addition to the and place application with removal, these that we want here, well, have do not apply is going to remove itself. It handles that on its own. But for an infinite effect, we're going to want to either remove it when we end overlap or simply never remove it. So we'll only have an effect removal policy for the infinite gameplay effect. So we'll go ahead and add that, and it's going to be infinite effect removal policy. And it gets a edit anywhere, blueprint read only, category applied effects. So now we have these application and removal policies, and we can check these when we apply our effects. So now we're going to need a different way to handle applying our effects, right? We're going to want to apply the instant effect by checking our instant effect policy, and if that policy is do not apply, then we're not going to apply that effect. And in fact, I think that do not apply is a pretty good default value for each of these. So I'm going to set instant effect application policy to effect application policy do not apply. I'm going to set all of them to this. So duration effect application policy do not apply, and infinite also do not apply. Application policy do not apply, and infinite also do not apply. And for the effect removal policy for the infinite effect, I'm going to give this one a default value as well. Now we could have it set to do not remove. I'm going to have it set to remove on end overlap by default. And now that I'm going to have it set to remove on end overlap by default. And now that we have these enums, I think we can have a pair of functions for when we begin and end overlap that we can call from the blueprint that can just handle these things. And really all this function needs is to receive a target actor. I don't think we really need to pass in the effect. We just need to have those effects set, and this actor can access its own effects. And before I make these two functions, I'm going to add a boolean so that we can destroy our actor after the effect has been removed if we want to. So let's make a bool first called bDestroy on effect removal. We'll set it to false by default, and we'll make it edit anywhere, blueprint read only, category applied effects, like so. And now we can add those functions that we want. So I'm going to make two functions, one for overlapping and one for end overlapping, and we'll just call these from the blueprint when something overlaps with whatever volume that we decide to add to our blueprint. So this will be a void function, and we're going to call this simply on overlap, and this is only going to take an A actor, and we'll call it target actor. And we'll also have an on end overlap that takes an A actor called target actor. And we can just call these from blueprint. So I'm going to make them blueprint callable. Give them the U function with blueprint callable. And I'll go ahead and generate the definitions for these. There's on overlap. Here's on end overlap. And we'll decide which effects to apply and when based on their application policies. And we're going to do that in the next video. We'll continue this then. So great job, and I'll see you in the next video. Okay, so now that we have an on overlap and an on end overlap function, we can decide whether or not to apply our various gameplay effects based on their application policy, right? So for the instant effect, we'll start with that one. It has its instant effect application policy. And if it's set to do not apply, well, we don't need to do anything. But if it's set to apply on overlap, we need to apply that effect in our on overlap function. And if it's set to apply on end overlap, we'll apply it then. So here in our application policy instead of apply play effect, we need enum effect here. Policy pair duration effect, removal policy, and based on it all. This is just about as simple as the more infinite effect on it. Let's go back to where handle be referencing once we've all video. Effects are removed. So the question is effects has handle active. So we can all can't just assume for any setting and losing requires a bit of gameplay effect applying and a to figure out an effect. I'd like to see. I'm going to take my we need to get that this game the game file dot. Now actually the duration has to look or not true in it. If we overlap removal by actor to be able to infinite effects. Now if infinite effect this up with expect it hand active it's not. I'm going to go ahead and include include at the top here, gameplay effect types.h. And that's going to take care of that effect error. Our gameplay effect handle and the target and here, which means I forward declaring equals there. And because if check matters when we plan moving, so we should be checked. We should not even bother storing it. Infinite will still at poly the infinite. So calling a plot, we can end overlap. See, that way we'll only do this if it's not pinned. Key here. Active effect. And so this results in removing the active gameplay effect from that ability system component that we linked up with it when we added the key value pair of effect handles to ASCs here when we applied the effect. So on overlap, we'll apply the infinite gameplay effect if the effect application policy is apply on overlap. And on end overlap, if our removal policy is remove on end overlap, the ASC, the active gameplay, which we do a couple changes, right? We have to go to our, so back here in the editor, we need to make a couple changes, right? For one, effect application policy, but we have an infinite effect. Welcome. In this video, we're going to make an infinite gameplay effect, which means our effect actor should have an infinite gameplay effect T subclass of. So we're going to go ahead and add one. On overlap, we apply an infinite gameplay effect. And the modifier is going to be infinite gameplay effect class. Welcome. In this video, we're going to make an infinite gameplay effect. So, and with that prints actor it, I'd like to have a folder link to, and here hit debug, compile, and launch. To blue organize these. A new type. And we'll call it target actor. From Blueprint, there's on overlap, effects to apply, and when we'll continue this next video. We'll continue this based on their application policies, and we're going to do that in the next video. We'll continue this then. So great job, and I'll see you in the next. And we'll decide which effects to apply and when based. Okay, so now that we have an on overlap and an on end overlap function, we can decide whether or not to apply our various gameplay effects based on their application policy, right? It's application policy. And if it's set to do not apply, well, we don't need to do anything. But if it's set to apply on overlap, we need to apply that effect in our on overlap function. And if it's set to apply on end overlap, we'll apply it then. So let's check this application policy in our on overlap function first. So here in on overlap, let's say if instant effect application policy is equal to E effect application policy instant effect to the target. So we have okay, so now that we have an on overlap and an on end overlap function, we can decide whether or not to apply our various gameplay effects based on their application policy. right? So for the instant effect, we'll start with that one. It has its instant effect application policy. And if it's set to do not apply, well, we don't need to do anything. But if it's set to apply on overlap, we need to apply that effect in our on overlap. Okay, so now that we have an on overlap and an on end overlap function, we can decide whether or not to apply our various gameplay effects based on their application policy, right? So for the instant effect, we'll start with that one. It has its instant effect application policy. And if it's set to do not apply, well, we don't need to do anything. But if it's set to apply on overlap, we need to apply that effect in our on overlap function. And if it's set to apply on end overlap, we'll apply it then. So let's check this application policy in our on overlap function first. So here in on overlap, let's say if instant effect application policy is equal to E effect application policy apply on overlap, then we can apply the instant effect to the target. So we have apply effect to target. We can call apply effect to target, passing in the target actor. And for the effect, we can use the instant gameplay effect class. And if we set this to apply on overlap, we'd better be sure that our gameplay effect class is set. Otherwise, we'll get a crash thanks to that check. So that's just something that we need to keep in mind. We can't set this to an incompatible enum constant if we don't have an instant effect to apply. Now, what if our instant effect has its policy set to apply on end overlap? Well, then we do it here. So we can place a check in end overlap if instant effect application policy equals E effect application policy apply on end overlap. Then we can call apply effect to target, passing in the instant game. Gameplay effect class. So that takes care of applying our instant effect, and that's the most care of applying our instant effect, and that's the most simple case. Now, the next effect in duration policy would be duration effect, because a duration effect removes itself. We don't have to check its removal policy or anything effect, and that's the, so that takes care of, because of anything like that, we just here in on overlap or end overlap based on its policy. So we can check that just like we did for the instant effect. We're going to say if duration effect up, and if it is, and this time the duration gameplay effect class. We'll do the same exact thing in end overlap if the effect application policy this time is apply on end overlap. So that case is just about as simple as the instant effect. We apply it and it removes itself. Now, the more complicated case is the infinite effect, because the infinite effect can be removed. And we want to remove the infinite effect on end overlap if we've given it to the actor in question. So how do we remove the effect? How do we know on end overlap that that actor has the effect? How do we check that, and how do we remove it? Well, let's go back to our code for apply effect to target. How are we applying the effect? We're first making an effect context. We're using the effect context handle and the gameplay effect class to make an outgoing spec. That gives us a spec handle. Then we apply that gameplay effect spec, getting the spec from the handle, dereferencing the pointer, and passing that in. So the question arises, how do we remove the effect once we've already added it? And we'll handle that in the next video. so now that we have an on-overlap and an on-end overlap function, we can decide whether or not to apply our various gameplay effects based on their application policy, right? So for the instant effect, we'll start with that one. It has its instant effect application policy. And if it's set to do not apply, well, we don't need to do anything. But if it's set to apply, and if it's set to application policy, say, so here in application, the install effect, our game is compatible. Now, what if well, then we affect application? So the most simple duration effect, because a duration effect that apply the duration effect overlap. And if it is, we'll call apply effect to target, passing in target actor. And to apply need to for our infinite and remove that effect on end overlap if we need to for our infinite effect. Go back to where we're applying effects. We have apply effect to target and apply gameplay effect to self has a return type. It's not void, it's F active gameplay effect handle. So once you've applied a gameplay effect, that gameplay effect becomes active, and these apply functions return a handle to that effect. So we can always use that handle for something later, such as removing it if it's an infinite gameplay effect. So we need to store this handle. Now we need to be careful about the way we do this. You see, if we're just thinking about one player character in the world running around picking up these effect actors, well, then we could store the active gameplay effect that we've applied, and then on end overlap, just take that other actor and remove that active effect. But realistically, games are not that simple. We might have multiple actors overlapping. Some of them may have ability system components, some may not, and we can't just assume that target actor in end overlap is the correct actor for any given effect handle. And if multiple actors are overlapping and we're setting a single effect handle variable, well, then we're overwriting it and losing the effect handle that variable stored before. In other words, this requires a bit more care. Now, one approach is that as we apply a gameplay effect, if that gameplay effect is an infinite duration gameplay effect, we can store the handle, but we can also store the actor that we're applying this effect to, essentially linking the two together. A map should come to mind. Map data structures are great for linking two values together. Now we can make two functions, one for instant and duration effect application, and one for infinite. But in the name of education, I'd like to show you a way to figure out whether or not this gameplay effect is infinite duration or not. In other words, check at runtime the duration policy for a given effect. I'd like to show you how to do that. Now, in order to check the duration policy, we have to take a look at our effect spec handle. So I'm going to take my effect spec handle, and from this handle, we know that the handle has a data member. So we can access that, we know that much. And data is a t-shared pointer. To get that raw pointer, we can call .get on that, and that returns us a pointer to f gameplay effect spec. Now this is the effect spec. What we want from the effect spec is the gameplay effect itself. Now, this pointer can be dereferenced, and the gameplay effect itself is called def. So inside the spec handle, we have data. That's the gameplay effect spec. Inside the spec, we have def, which is the gameplay effect. Notice it's a t-object pointer of type uGameplay effect. Now, this being a t-object pointer means we have to call .get yet again, and that gives us the raw pointer, which we can access to get all of these things on the gameplay effect itself. And one of those things is duration policy. Now, keep in mind, we're accessing the class default object properties here, and we don't want to use this method to, say, change the duration policy at runtime, for example. No, that's not what we want to do. This is just to look and see what the policy is. And we're assuming that this policy isn't changing at runtime. Well, we can check it, and we can see if it's equal to an eGameplay effect duration type, as that's what the duration policy is. It's an eGameplay effect duration type, and we can check to see if it's infinite or not. Now, if it is infinite, well, then we know that this expression will return true. So we can create a const bool called b is infinite and set it equal to the result of this. Now, if we wanted to be able to remove duration-based effects on end overlap, we could then give our duration-based effect its own removal policy, just like we have for infinite. And that just depends on what you'd like your effect actor to be able to do. This effect actor that I'm making will only be able to remove infinite effects, and they'll only be removed on end overlap. Now, if it is an infinite effect, I want to store this infinite effect somehow. And how do I store it? Well, apply gameplay effect spec to self returns an active gameplay effect handle. That's what I want to store and link up with the target actor. So the return type from apply gameplay effect spec to self and f active gameplay effect handle, I'm going to store in a local variable called active effect handle. And if b is infinite is true, then I'll store it. So I'm going to say if b is infinite, then store the effect handle. And I'm going to store it in a map. And the map can map f active gameplay effect handles. And the value can be the target actor, or even more handy, can be an ability system component. That way we don't have to dig into the actor to get the ASC. We have the ASC already. So I'd like to make a map mapping active gameplay effect handles to ability system component pointers. So let's make that map. So I'm going to say tmap, and the types will be f active gameplay effect handle. That's the key. And the value will be u ability system component. We'll add the forward declaration, and that'll be a pointer for that type. And we'll call this active effect handles. And we know it's mapping handles to ability system components. Now we're not forward control shift fire, and that tells me, and that's going to take care of that compilation error there. Our gameplay effect is infinite, the f active gameplay. So I'll take active effect handles, and I can add this key value pair. It's going to be active effect handle and target ASC. And I get the red squiggles and target ASC. And I get the red squiggles, so I have to come back here and check for typos. It looks like I have UAura ability system component. That's not what I want. I just want ability system component here, which means I forward declared the Aura version. I don't want that. So I'm going to make sure I'm only forward declaring the base ability system component. And that's going to get rid of my red squiggles there. So an easy mistake to make. And writer says the active effect handle can be const. We can make it const if we like. B is infinite, can be moved inside this if check if we want as well. I'm going to leave it out and keep it like this as a matter of style. So active effect handles now has a key value pair. When when we apply an effect to a target. Now, we should only be doing this if we plan on removing the effect, right? If we don't plan on removing the infinite effect, then there's no need to store a handle to the effect. So we should be checking that, right? If we don't plan on removing the infinite effect, then there's no need to store a handle to the effect. So we should be checking our removal policy. If it's do not remove, we should not even bother storing it. But if it's remove on and overlap, we should. So if our effect is infinite, we'll also have an and here, and we'll check our infinite effect removal policy and see if it's equal to E effect removal policy, remove on and overlap. If that's the case, well, then we'll store it. And then on and overlap, we'll remove it, but we'll check that policy as well. So in on overlap, we have to apply the infinite effect, and on end overlap, that's where we handle removing it. So first we'll check to see if we should apply it. Application policy, we'll apply target actor, but we can change this. So we'll infinity, what do we will, and the target that ability. First we have to get the system. Do it that way. You pair if there's an A component that we'll call mapping. So you could just copy that and then replace auto with handle pair into my target ASC. So we're going to check place here, call active to this. So we'll say if policy apply on overlap to target. Calling apply effect to target. Want to check that ability system component. But we'll say if is valid. Check if that's a valid component against our key value pairs in our map. So first we have to get our Well, first, because to get the against our key value pairs active effect handles. If you don't like using auto here, the type is right here. T tuple mapping F act. Copy that. Just take this pair and we're going to say handle pair play effect. And we remove it. Check to see if opponent pair hand that over opponent. So you could just copy that if you're in Writer, or just hover over it in Visual Studio and see what it is. Is take this pair handle pair. And see if target ASC, if they're equal. Using the and to remove gameplay effect. How about that? We have pair.key. So we're going to say handle pair.key. We remove the gameplay effect. We should problem. We're currently looping through. That's just begging for a crash. And accumulate like to remove after we're done with this for loop. In other words, we can make an array of the gameplay effects to, we're going to add that add, and we'll add handle pair. We'll loop through our array. So we'll make another for loop. This one can be auto reference. We'll call it handle, and we'll loop through handles to remove. And what are we going to do? We're going to remove that particular element from our map by key, because the key is an active handle. Gameplay effect F active. Moving that we ASCs here. The infinite gameplay effect is act. So it goes to ASCs here when we apply the effect. So handles that we link gameplay effect. And so an active gameplay effect handle. So if you don't want the auto there, you can explicitly state F active gameplay effect handle there. And so this results in removing the active gameplay effect from that ability system component that we linked up with it when we added the key value pair of effect handles to ASCs here when we apply the effect. So on overlap, we'll apply the infinite gameplay effect if the effect application policy is apply on overlap. And on end overlap, if our removal policy is remove on end overlap, then we'll check our map, see if it contains a key value pair that has an ASC that matches the ASC of the end overlap actor. If it does, we'll remove the active gameplay effect. And mark that handle to be removed from our map, which we do immediately after. So back here in the editor, we need to make a couple changes, right? We have to go to our BP fire area and change some of these properties. For one, we don't have an instant can be gameplay change to make a couple immediately after. BP fire area and change some of the class. instant effect application policy can be left at do not apply. Same goes for duration, do not apply. But we have an infinite effect, and the infinite effect application policy needs to be set if we want to apply the effect. I'm going to apply on overlap, and for infinite effect removal policy, I'm going to remove on end overlap, and we're going to remove a single stack. Now, if we wanted to remove a single stack or all the stacks, we could create a variable and expose it for that as well if we really wanted to. All right, and now the only thing we need to do is make sure to call our blueprint callable functions on overlap and on end overlap. That means we're not going to use our apply effect to target anymore. We're going to call on overlap, which takes the actor. We're going to pass in other actor, and we're going to take our box and get on component end overlap. And for this, we're going to call our end overlap function. And other actor here. Here into target infinite effect apply. So that's looking good. So why don't we give this a try? I'm going to press play. I'm going to overlap, and there goes my health. It's going down. And as I end overlap, it's no longer going down, which is exactly what I wanted to see. I'm going to do this with show debug on. I have 30 health. I'm in the fire. It's going down 20, 15, 10. And as I leave, it stays at 10. And this is looking great. We can even check the stacking for this. Let's just double check our stacking policy. Looks like our stacking type is none, but we can choose to aggregate by source or target. I'm going to choose target and set a stack limit count. Let's do, say, 3, and stack expiration policy can be remove single stack and refresh. So that way we can have up to 3 stacks at a time, and as we end overlap, we'll be removing those stacks. So why don't we duplicate this a few times? We'll duplicate it twice. So there's a point here where we might be overlapping with all 3, and I'll show debug, and if we're overlapping with 1, we should see our health going down by 5 at a time. If we're overlapping with 2, we should see it going down by 10 at a time. And with 3, we should see it going down by 15 at a time. So let's see if we can do that. Okay, we're going down by 5 and 35, 50, 65. Okay, we're going down by, looks like 15 at a time. And as I move away, those stacks get removed. So it's a little hard to see with such small volumes, but we get the gist. I'm going to go ahead and increase the size of these volumes to make it a little easier to test out. I'm going to take the box here and make its volume a bit bigger for this volume here. And I'll just duplicate this effect actor. So I'm going to go ahead and delete the others. So we'll have this one. I'll go ahead and duplicate it like so. And I'll duplicate it again like this. So that way we have an area here where we'll have 1 stack, an area here where we'll have 2, and an area in the middle where we can have 3 stacks. So I'll turn off hidden in game. Okay, so I'll press play. I'll show debug. If I go into this area here, 35, 30, 25, 20. So we're losing 5 at a time. Now I expect to lose 10 at a time in this area, and I have negative 40, negative 50, negative 60, and so on. And as I go into this area, I should see negative 115, negative 130, 160, 175. So it's as expected. Now here's the thing though, if I have 3 stacks and I leave one of these volumes, all of a sudden we no longer get any changes to health. We removed all stacks, right? And that's because removing the gameplay effect removes them all. But what if we only want to remove a single stack? Well, let's close the editor and go back to our IDE where we're calling remove active gameplay effect. If I hover over it, I see that the first input is the active effect handle, but the second is an int32 called stacks to remove. Now it has a default value of -1, and if we don't pass anything in, that -1 means remove all stacks. But if we want, we could remove a single stack. So for example, I could place a comma here, and we could simply remove 1 stack. Now we may have multiple effect actors, and each has their own map, right? So each one should really just remove a single stack. Do that. So let's hit debug and try this out. All right, I'm going to open my blueprint assets, and to make testing really easy, assets, and to make test modifier magnitude -1. That way I'll know if I have 1 stack, 2 stacks, or 3 stacks. Let's give this a try. Know if I have fire magnitude assets, and to make testing, all right, I'm going to open my blueprint assets, and to make testing really easy, I'm going to make my fire area modifier magnitude -1. That way I'll know if I have 1 stack, 2 stacks, or 3 stacks. Let's give this a try. So I'll press play. I'm going to show debug. I have 50 health. Going into this area, it's going down by 1 per second. Now overlapping 2 of them, it's going down by 2 per second. Going into this one, we have our health going down by 3 per second. Now if I go into the 2 area, and we're now going down by 2 per second, and going into the 1, we're going down by 1 per second. So we're only removing a single stack at a time. And gone past 0 health. We're going into the negatives, which we shouldn't be able to do. We're going to learn how we can implement clamping for these effects soon enough. But for now, we know that we can have multiple stacks of a single gameplay effect, and this allows us to make any number of gameplay mechanics that apply effects. So this is pretty great. Now, I'm going to go ahead and just delete these fire areas, because what I'd rather have is an area in which I don't start losing life unless I can see fire there, right? We just made that box visible for debug purposes. I'm going to turn off hidden in game, or rather turn it back on, and we can have multiple fire areas. So say I have one here, and one here, and one here, and that way we know that this is dangerous to be in. And if we get out of it, we stop getting hurt, right? And we just happen to be able to stack these as well. And you could make a super fire area if you wanted to by making the overlap volume bigger. Let's just demonstrate that. We'll take the box extent and make it a little wider, maybe like this, and we can have multiple fire effects. So we can add a Niagara particle system component. We can call this one fire underscore 2. We can move it around, set it to fire. We'll just have 2 for now. I think that's enough. And I'll make this volume encompass the area. So let's squeeze it in like that. I'll make this fire effect right here and this one here. Like so. There. And now we know if we step in the fire, we'll get hurt. Excellent. So our aura effect actor is quite versatile. We can use it the way we used our overlap and end overlap functions in fire area, or we can use it like we did our health potions and just call apply effect to target directly. We have control here in Blueprint, and it gives more flexibility to the designer side of things. Okay, excellent job. So now designers here and fire. Well, if we step in the fire, oh, there. And now we know if we squeeze it in like that, I'll make this fire effect or 3 stacks. Let's give this a try. So we've long since gone to 2 this or 3 stacks. Let's give this a try. So I'll press back 2 stacks or 1. I'm going to make that way. I have 50 health going in. I'll go ahead and duplicate it. So that way, as we end, why don't we duplicate this a few times? Our health going down by 5 at a time, and like 50, move a little hard. I'm going to go ahead, easier to bigger for this. So I'm going to go ahead and duplicate it. This, I'm going to go ahead and duplicate it again like this, where we'll have 3. I'll show debug 25, 20. If I go into the, so I'll press show debug. I go into the middle where we can have one stack. So that, I'm going to go here, make the box here, and make its volume a bit bigger for this volume here. And I'll just duplicate this for this. Those stacks get removed. So it's a little hard to see with such small volumes, but we get the gist. I'm going to go ahead and increase the size of these volumes and make its volume a bit bigger for this volume. I'm going to take the box here and make its volume a bit bigger for this volume here. And I'll just duplicate this effect actor. So I'm going to go ahead and delete the others. So we'll have this one. I'll go ahead and duplicate it. So that way, we have an area here where we'll have one stack, an area here where we'll have two, and an area in the middle where we can have three stacks. So I'll turn off hidden in game. Okay, able to do, we're going to, but for now, we know we stop getting hurt, right? And now we know if we step in the fire, I'm going to give you a side quest. Now, these are like you to create arrays of each duration type and figure out how to here. And that way, we know that this is dangerous to be in. And if we get out of it, we stop getting hurt, right? And we just happen to be able to stack these as well. And you could make a super fire overlap box and have multiple particle system underscore 2. I'll make this fire like so. There. And now we know if we step in the fire, we'll get hurt. Excellent. So our aura effect actor is quite versatile. We can use it the way we used our overlap and end overlap functions in fire area, or we can use it like we did our health potions and just call apply effect to target directly. We have control here in Blueprint, and it gives more flexibility to the designer side of things. Okay, excellent job. So now I'm going to give you a side quest. Now these are optional, and I won't be giving you the solution. For the side quest, I'd like you to create arrays of each duration type and figure out how to handle that. And then post your solution in the GAS top-down RPG channel in the Druid Mechanics Discord. So instead of applying a single effect, you're going to apply an array of effects and make sure you figure out how to handle removing all of those effects. And if you can manage to get that working, post that in the Discord. Side quests, again, are optional through the solution for them. That's totally fine. Just continue with the course. We won't be using anything in the side quests. Welcome back. Now we're changing our attributes, and we've seen that our health can go into the negatives, and we can also fill up our health bar and continue increasing health. Same goes for mana. In other words, we're not really enforcing any clamping. Now there are different ways to enforce clamping, and in this video we're going to learn one of them. We're going to go into our attribute set. So I'm going to open my public folder, go to ability system, and open Aura attribute set. And here in the public section, I'm going to override one of the functions that we've inherited from the attribute set class. So it'll be virtual, and it's a void function, and the function I'm interested in is called pre-attribute change. Now, Writer is offering to fill out the rest of it for me, so I'm going to go ahead and let it do that. And as you can see, it takes in a const reference of a gameplay attribute, the fGameplay attribute struct, and a float called new value. And notice the float is passed in by reference, and it's not a const reference. That should hint to you that we can change new value, and something somewhere is going to change. Now, let's go ahead and generate this definition and let it call the super version of pre-attribute change. And I'd like to just see what happens in this function when we gameplay attribute and see if there's an audio override, say attribute is our health attribute. Now, when any of our attributes change, whether it's from a gameplay effect or from being set directly, this function will kick off in response. And it's called pre-occurs, but that's and educational purposes, what template attributes we have. So I'm copying it and changing this to get max health attribute and changing the comment to say max health, and I'll copy both of these, and instead of health we're going to change it to mana. I'm just going to hide for health, and I can replace health. Now these are the mana versions. Okay, cool. And in Visual Studio, just make sure you know what you're, and now we're seeing when any of our attributes and see what we get printed, and I'm ready to test our own. And these are instant gameplay effects, which means we know that they permanently change the base value of those attributes. Now, we also have these crystals, and these are different. They have duration, and they also are periodic. Now, because they are periodic, they act like instant effects. So they also permanently change the base value. We also have area. The GE fire area is periodic as well. So all of these affect the base value permanently because they're either periodic or instant. Now let's open the output log. I'm going to dock it in the layout and bring it down here so that I can see it. And I'll go ahead and press play. And let's see what happens if we pick up a mana potion. Here we see warning mana 40. Let's pick up the health potion, and it says warning health 75. I'm going to show debug just so we can compare and make sure that these are correct. And sure enough, they are. Let's go into the fire volume, and we see that our health is going down by, looks like 1 per second as expected. And let's go ahead and pick up a mana crystal. And we see it going up, and let's pick up a health crystal, and we see it going up. So as we can see, we have pre-attribute change being called in response to these attribute changes. Now here's the thing, it's called pre-attribute change, which means we have the opportunity to perform some sort of clamping before the change occurs. So if we change this new value, well, what happens? Right? Because we see that it's passed in by reference. So is that going to actually change our health to value? And let's say as our health value changes, it'll never go below. So down here, if it's new value but clamped between 0 and instead of max health, we'll say max mana. Like so. Now let's go ahead and run in Press Play. I'm picking things up. I'm going to pick up a health crystal. We go up to 20. Picking another one up, we go up to 30. Another one, we go to 40. Pick that up. Look at that. We actually stay at 50. Now that mana potion does work, right? Let's pick up the mana potion. If we pick up a crystal, we go up to 50. But if we pick up where the attribute changes, we have the and we can't above. Go. Just gonna test. Is it enough to push me over? No, but attribute change. Check. It's really just meant to clamp. And that's what we're going to use it for. So before the attribute changes, we can perform clamps. I don't really feel like I need all of these logs. And I'm not really going to clamp our go below 0 and remove that. I'm going to leave our clamping for health and mana. I think those are useful. So we'll go ahead and leave. Here we can modify the changes to the change actually happen through attribute function, fire the attribute. In other words, we can clamp changes before the pre-attribute change. And these will either opt value the attribute macros, attribute pre that, and for health and mana. I think those are useful, so we'll go ahead and leave those. So pre-attribute change of an attribute is we'll go ahead and leave our clamping for health and pre-attribute change is where and this is triggers that we've literally anything that changes the attribute can trigger this function. Now this does not permanently change the modifier for a given. The modifier happens, and these will recalculate health changes, for example, for errors in change. But an change changes whether that's through attribute and leave those. So pre-attribute change is where we can modify the changes to the current value of an attribute, and this function is called before the change actually happens. Now that is a significant detail, and we'll see why in a second. Pre-attribute change is triggered by changes to attributes, whether that's through attribute accessors like the setters that we've created thanks to our boilerplate macros, or due to gameplay effects. Literally anything that changes the attribute can trigger this function. Now, this does not permanently change the modifier for a given attribute. It just changes the value returned from querying the modifier of the attribute. In other words, we can clamp changes before the change happens, but there are later operations that happen after pre-attribute change, and these will recalculate the current value from all modifiers involved. So if the value of health changes, for example, for any reason, then there are later operations that will recalculate that health change, which means that our clamping will have no effect. And we'll have to clamp again later on. So pre-attribute change is not the most attractive choice to implement final clamping changes, but it is there. Now, you may be curious as to what might be the best function to implement something for when an attribute changes, and be sure that that change will be final. One of those functions is called post-gameplay effect execute. This actually happens after a gameplay effect has changed an attribute, and we're going to learn about this function in the next video. I'll see you soon. Welcome back. Now, we've just overridden a function called pre-attribute change, and we've used it to perform some clamping here in the attribute set. Now, pre-attribute change is really only good for clamping. It's not really good for kicking off any logic in response to attribute changes. But that's not to say that we can't do that. This is just not the place for it. Now, there is another function that's extremely useful for the attribute set, and we're going to override that now. So let's say virtual void, and the function is called post gameplay effect execute. Let's go ahead and get that declared. And we see that it takes a const reference called data of type f gameplay effect mod callback data. Now, I'm going to generate the definition for this function and let that super call exist. And now we have post gameplay effect execute. Now, post gameplay effect execute is pretty self-descriptive. This is executed after a gameplay effect changes an attribute, and we have data input parameter. We can access it. And we're going to harvest some information from this data and accessing evaluate. So already we're seeing some really evaluated data. If we type the f is being changed here and use comparison, we'll compare it to that attribute. And if it is the health attribute warning with get health count changed, and I'm going to magnitude evaluate how much we're changing the health. Let's just test this out. I'm going to hit debug, and we'll inspect it printed to one. If we pick up the health potion, we see that we go from 44 to 69. Magnitude of that gameplay effect was 25. Here we got our mana. That attribute is 1 each time. You get the gist. Breakpoint. We'll place it right here on the UE log. Okay, so what I'm mostly interested in right now is data. And right here at the bottom right, effect spec, evaluated data, and target. Now, if we expand or def GE object from the actual handle, the F of our target component of this game, of the target, both the owner actor. So not only can we affect spec context, and the context has information about the source if we set that. Here's the effect context. In its data, we have instigator. In this case, it's the aura player state. We have the effect causer, BP aura character. These are just set in the effect context because the effect context was created in this case. So set on whatever actor is over to be really the ability system component when aura and then the enemy that gets hit. We have access to this gameplay of thing, the gameplay effect. We can even store them all in a data. Do in this video is nice learning attribute. We can use this to execute it. We're going to start collecting here, and I'm going to go ahead and remove the breakpoint and remove this code here. So if we take data and we get our effect spec from the effect spec, we can call context handle. System component, source and target, equals parentheses, right? The targets back to us. So context system ability system component hover over auto, but ASC ability system other things, perhaps called source component, and that valid some checks in place. We'll say C ability actor dot is valid. So you're here, and then wrappers t zone utilities is pointer stored in avatar actor is valid if all the actor. So we'll the player controller of the source if their info as well. We can say that's valid. That weak object point this. It's a player called source. Now here's the thing for the player control. The actor's check will center, and that is not the player control on source actor. And we now get controller, player controller, or an A control. I'll just call it source actor to a source control. So you have on the source. If we can make the A controller, change it later. We can, but either way, we know info. But if ability act from the actor, by optional second step there, we can also access the source character that may or may not be null as well. So we can say if source, then we can get character, and we can say cast. So you're going to be thinking, and the answer is yes. Possessed pawn. You can cast. So I'm casting to with get pawn. The character up at the teamwork. Keep info here that we got the opponent. So how are we going to get the bottom if we take our data component? We also have the target ability actor dot target and a weak object pointer dot target and info checking using. Then we'll set a controller target going to be cast a character actor. To access these, passing in target actor. You ability system get it that way. Execute using this all throughout. Execute with all of these and collect all of these effect system components. By the way, this should be called target actor. We have kind of struct function retrieve them for this video. I'd like you to create the effect set header file. The controller definition. For now, I'm not going to grow. I'm going to call it source property. Deal with all the sort. So a actor null pointer. That's going to be the null with u. Call it with u property. Copy all of them and can replace it with versions. That properties. Control KO effect executes and cut it out. And now so let's take a look at context handle right here. Set propping. Now we can set source AS now stored on source ASC as valid. A source AS in here. Place this with props. Source prop our source all over the pointer. Okay, and variable on props and target character who's the one on props using and set effect be a constant function. Quick, just add that effect properties is packaged up in properties which we can pass in to all effect video. And we've used it to perform some clamping here in the attribute set. Now pre-attribute come back to change. And we've used it to pre-attribute change logic, and this is just not the place for it. Now there is another function that's extremely Welcome back. Now, we've just overridden a function called pre-attribute change, and we've used it to perform some clamping here in the attribute set. Now, pre-attribute change is really only good for clamping. It's not really good for kicking off any logic in response to attribute changes. But that's not to say that we can't do that. This is just not the place for it. Now, there is another function that's extremely useful for the attribute set, and we're going to override that now. So let's say virtual void. And the function is called post-gameplay-effect execute. Let's go ahead and get that declared. And we see that it takes a const reference called data of type f gameplay effect mod callback data. Now, I'm going to generate the definition for this function and let that super call exist. And now we have post-gameplay effect execute. Now, post-gameplay effect execute is pretty self-descriptive. This is executed after a gameplay effect changes an attribute, and we have access to a lot of information via this data input parameter. We can access all. And we're going, for starters, we're going to take our data and access back, and that evaluate, you'll see that we have some. So what we know from the data which attribute is being changed here. For example, we can wrap this in an if statement and use comparison and see if the attribute is equal to, for instance, get health attribute. We'll compare it to that attribute, and if it is the health attribute, we can just place a UE log here. I'll use log temp warning. Health tude, or the, I'm going to print that out as well, so I'm going to copy and paste data. If that thing up information now, right, to have information. See, so that's the gameplay effect. 1. So not only can we get information about the target, we also can get information about launches a fireball at an enemy. She's going to be by getting our effect context. So if we take data and we get our effect spec, from the effect spec, we can call the function get context. And this returns an f gameplay effect context handle. We're going to store context handle the system component. From the source of this gameplay effect. And by the way, when I say source and target, just so we don't get confused, I'm just going to put a quick comment here that says source equals call. Causer of the effect, and then target equals, well, target of the effect, but in parentheses, owner of this attribute set, right? The target is the thing being affected. In other words, this attribute set's owner, right? The source is something else, right? The source weighs the A equals type, but ASC isn't a component, such as the source actor. That owns that ability system component. Perhaps it's the avatar. So we can make an A actor called source avatar actor. For example, and we can get the ability system, and that has the avatar actor. And of course, this is a pointer wrapper we have to call. Get on that pointer. Okay, so we're doing a lot of accessing of pointers here, and not all sources may have a valid ability system. Say we're using ability actor info with the dar, which functions, and make sure that the pointers, if that or from the ability actor info, have to call get to get that controller, so we can make info has a null. Null pointer for the player controller, we can always fall back on getting the player controller from the actor itself by casting it to a pawn. The player controller is a null pointer in that case. and our source avatar actor is not a null pointer, then we'll attempt to get the player controller from the pawn directly. So we'll perform a cast here. We'll say if a pawn equals cast to a pawn source avatar actor. If that cast is successful, then we now have the pawn we can call get controller using pawn get controller, and get controller returns an a controller, so we could just cast a player controller like this, or if we want the controller and don't care if it's a player controller or not, we could just call this source controller and make it an a controller instead. We can always cast later if we need it to be a player controller. I'll just call it source controller, and if we cast source avatar actor to a pawn, then we don't need to cast. We'll just say source controller equals pawn. The source may not be a pawn. The source may not have it. We can make the a controller const here. Later we can change it later. This can be made const the effect context handle as well. But either way, we know that we can access the controller. So what we're doing is we're contain the act option. Know that we have the pawn. We can also at this point we have a source controller that may or may not be character as well. So So we can say if source controller is not null, or just if source controller, then we can get the source character. We can say a character, source character, and we can cast the pawn possessed by the controller to a character. We can say cast a character. And by the way, as I'm doing this, you're going to be thinking in your mind, can't we do this another way? I can think of 3 different ways to do it. And the answer is possess. There's a lot of source that says of the framework, character.h. Ours. Ability system, we're going to get bottom if we take the system component. So there it is. And we can easily store that here on that avatar actor. I will say if data, the actor info, avatar, and using those point target actor ability actor. Info player controller. And that's going to be .get, of course. We can get the character. Ability system component, right? Here, component, that was gameplay effect, execute, using this all throughout. Execute with all of these these lines of code, rather than cluttering up post-game all throughout the court. All sorts of information, and we're execute from data. We have the ability to get all sorts of information, and we're going to be using this all throughout the course. So rather than cluttering up post-gameplay effect execute with all of these lines of code, it'd be handy to refactor a handy little function that can collect all of these into perhaps a struct or something like that, or target avatar act. We should specify so we don't confuse ourselves. So target avatar actor in some kind of struct, and then in post-game putting the properties based on the effect. That's kind of the, so here's your quest. You can define the property owner that way. Effect property. Go ahead and here at the top, we'll define our struct. I'll put it below. And right here at the top, we'll define our struct. I'll put it below the attribute accessors properties. And I'd like it to be a uStruct. So I'm going to add the uStruct macro. For now, I'm not going to make it blueprint type or anything like that, but I do need the generated body macro. Takes no argument. The effect effect, and I'm going to make sure to initialize them all to null. Call it source ASC and initialize it to null pointer, and give it a U property. And it's just going to be an empty U variables first. So we'll have source, give it a U property, and an A, make that a null pointer as well with U. So I'm going to copy all of these four and control place it with targets. Now I'd like to make a function for an F effect, and we're going to put it way down in a private section because this is it's going to be a couple of things: the CPP file effect and private section here on const reference properties struct. As a non in the attribute set. I'm going to put it way down in a private section because this is just internal. If I Alt O or Control K O into the sequence reference the data to, and of course, const because it'll be an F effect. Important that it's a non-const reference. And we'll generate props. This will be pass in. So we're going to need to pass that in. And that's where we're getting all this stuff. Properties. So I'm going to paste that right there. Back properties. Fill it in with all, we'll just call it props. Very important. that it's a non-constant this struct. We're going to fill it in with all the data. So this will be an F effect properties reference called, we'll just call it props. Very important that it's in this and reference. And we'll generate the definition, and I'm going to effect execute. Use all the code we've already done and paste it in to set our props struct. Store the effect context handle. Let's get that stored in our props struct. We have it right here in a local variable. Now all we should really have to do is set props.effect context handle. Do is set props.effect context handle. So that takes care of the first thing. Now next we have the source ability system component stored in our props struct with handle. Let's get that stored in our props struct. We have it right here in a local variable. Now all we should really have to do is set props.effect context handle. So that takes care of the first thing. Now next we have the source ability system component source AS first thing. Now effect context handle. So that takes care of the first thing. Now next we have the source ability system component source ASC. Well, we can set that on props, so we can just replace this with props props.source ASC. Of course, we have effect context handle here, but that's now stored on props. So we're going to want props. Effect context handle there. So we've got our source ability system component. Now next we're checking if source ASC is valid, but now it's in our struct props.source ASC. So we're going to replace source ASC with props.source ASC here, here, and here. Next, we're getting the source avatar actor from source ASC. We're going to replace that with props.source ASC, and source avatar actor is also on props. So we're going to replace our local variable with props.source avatar actor. We're going to set that on our struct. We're going to do the same thing for our controller. We're going to replace this with props.sourceController, and source ASC is going to be props.sourceASC. And we're going to check props.sourceController here and props.sourceAvatarActor, and then we're going to cast to upon our source avatar actor on props. So we're just pasting props dot all over the place. Same with the source controller here. We're going to set that there, and then here we're checking that pointer, and then we're replacing source controller with the one on the props struct. Okay, so next, we're going to get our variable set for the target. target. And first we have target avatar actor, and that's of course a variable on props. So we're going to set props.target. Avatar actor here. And also target controller is going to be set on props, and target character is going to be set on props, and it's casting target avatar actor. We're going to use the one on props. And then we have the target ASC. We're going to set that on props using target avatar actor, passing that into get ability system component. And now we've set those variables for the target. So now we have this nice function set effect properties. And as always, Writer is reminding me that this could be a const function. And why not? I'm going to make it a const function. And because I can, real quick, just add const to it, like just add water, just add const. And now we can call set effect properties here in post gameplay effect execute. And we have all of our data just packaged up into our props struct. So what I'd like to do is make an f effect properties struct called props, and then pass it into set effect properties, which takes two things, the data, which we can pass in, and the props, which we can pass in. And now from within post gameplay effect execute, we have easy access to all of these properties. We can get props.source character, source controller, target, all of these things. And we just have to keep in mind that depending on what caused the effect, it might not be a character that caused it. It might not have a controller. It might have some of these properties and not all. So it's important to check if those are valid before you have access to Discourse. Excellent job. We now see you in the video. It's going to be very useful for us, and I'll see you in the next Welcome. Now we're just about done with this section, but that doesn't mean we're done with gameplay effects. There's still a lot to learn, and we're going to learn more about them as we incorporate them with the other elements of GAS. But one last thing I'd like to touch on before we move on from this section is the fact that we've been using these scalable floats. Let's go back to one of our gameplay effects. I'm going to go into our potion folder. Into GE Potion Heal and scroll down to our modifiers where we have one that changes health by adding, and our magnitude calculation type is scalable float. Now so far we just hard-coded a single value in here, and that may seem that that's all that scalable float is good for, but we have this curve table dropdown. Now, yes, when we click it and expand it, it's empty. But that's just because we have to make our own curve tables to use here. And that's what this video is all about. We're going to make a curve table for our GE Potion Heal. You see, gameplay effects have the concept of level. Lots of gas elements have the concept of level. Abilities have levels, gameplay effects have levels. So the curve table gives us the option to scale our magnitude by some value based on the effect's level. So let's make our curve table. We're going to go into the potion folder. We'll just make it right here, and we can go to miscellaneous, and there it is, curve table. We're going to choose curve table, and we can use linear, constant, cubic, and this is just the mathematical function that our curve is going to take on. For now, let's try linear. I'm going to create the curve table, and I'm going to call this CT for curve table, potion heal. And open up CT Potion Heal. Now, a curve table is quite simple. It's sort of like an Excel spreadsheet. In fact, right up here, there's two different options. We have the graph view, and if we click on that, we can see what the curve looks like as a graph, but there's nothing there yet. We still have to make the curve. But going back to this view, it's more like a spreadsheet. Now, if we click on this triangle here, this view, there's nothing we can see. We have, in fact, is quite simple. It's potion curve here. I'm going to create the curve table, and I'm going to expand up a view, and if we click on that, we can see what the curve looks like as a graph, but there's nothing there yet. We still have to make the curve. But going back to this view, it's more like a spreadsheet column, and the column has the value. We see that there's a column, and the column curve has the value 5. Let's add another row, and for 2, 8 will make it. This gives us a curve that we can use for our healing curve. We're going to select, for example, we can call this 1 now. Now, here we can go to the Potion Heal. So, let's go back. So we basically can see we have the graph view, and if we click on that, we can see what the curve looks like. But going back to this view, it's more like a spreadsheet. Now, if we click on this triangle here, then say, and for 2, almost an X made. Let's go back into. So we basically have this really simple curve. Now look at what we've made. Go back into graph view and select the curve. Now look at what we've made. Our curve looks like this, and it's kind of almost an exponential increase. It's linear, but we chose the values. So in between each value is linear, right? So this gives us a curve that we can use for our GE Potion Heal. And if we go back to GE Potion Heal, and go to the scalable float magnitude, we can use the curve table. We can open the drop down, and there's CT Potion Heal now. Now, here for scalable float magnitude, we can select a curve because a curve table can have multiple curves. As you can see, we can add a new curve by hitting the plus curve icon there, but so far this just has one curve. We can rename the curve. For example, we can call this healing curve. Let's save that. that. And back here in the gameplay effect, when we go to select the curve, there's our healing curve. We're going to select our healing curve. Now, we can preview the value that we would get right here based on the level. And we can go all the way up to level 10 because that's how far our curve goes for healing curve. So at 10, the reason we're getting 2,500, and if we go back down to 1, we're getting 125, is because this value that we put right here is scaled by the value on the curve for that level. So at level 1, our curve has the value 5. So it's taking 25 at level 1 and multiplying by that curve value 5. So if we want these literal values here, then we'd have to stick a 1 right here. And then at level 1, we have 5. At level 2, we get 7.5. Basically, those numbers that we put into our curve. So that's what this little preview slider is good for. So we know that our potion is applying our instant gameplay effect at level 1, right? So we can press play, and we should be able to pick up a health potion, and we'll see an increase of 5 for our health. So our health is at 50, picking it up, now it's at 55. Right? Pretty simple. But what if we'd like our health potions to have their own sort of concept of a level? What if we want our effect actor to have a level itself? And then it'll apply all of its gameplay effects at that level. Now, you could have multiple levels, one for each duration type. There's no end to the complexity you can make these things, but I'm going to just say that our effect actor has its own level. We'll call it an actor level. And that's a variable that I'd like to add to the effect actor in C++. So I'm going to save all, close out of the editor, and go back to my effect actor. I'm going to open up the actor folder and Aura effect actor, and I'm going to add a new variable. Now, these are all protected, and I think the actor level can also be protected. So I'm going to stick it down here at the bottom. It's going to be a float. So I'm going to call this float actor level. And I'd like it to be edited anywhere that you probably enough. So if we want, we can have non-discrete. Now our actor Alt-O will open Aura effect actor.cpp, our effect, and we'll make outgoing spec. We play effect spec here, right? And level is float or level. Now we can go in into the blueprint and change the level and make our potion or whatever type of effect actor more or less powerful based on the level. Perfect. Let's hit debug and we'll change the levels of some of our potions and see how they work. Okay, I'm going to click open. That's just going to bring up my CT potion heal curve table. And I'm actually going to open my BP health potion. Let's get that open and let's see if we can find that actor level. Here it is, and it's set to 1. You know what? That's fine. I'd like to drag in a couple of these next to each other, each at different levels. So the default value is 1, so that's going to be at 1. I'm going to copy one, and this one I'm going to set its actor level. Let's set that to 2. Let's copy another one. We'll set this one to 3. And why not? This fourth one can be 4.75 because these don't have to be integers. So let's test this out. I'm going to press play. I'm going to show debug ability system. I'm at 50 health. I'm going to pick one up, and I get 5 more, so I'm at 55. Picking up another one. Oh, look at that. I'm at 6250. I got 7.5 added. Picking up another one. I'm at 7250. Looks like I got 10 added. Now this one I'm going to pick up, and I'm at 91.25. So because this one has a level, if we take a look at our curve for healing curve and find 4.75, it's somewhere right here between these two vertical lines, then we're here, which is about 18.5 between these 2 points. Pretty cool if you ask me. Now here's the cool thing. We know that our potion heal curve table can have multiple curves, right? Well, why can't we just use one curve table for all of our potions? So that's kind of what I'd like to do. And that means I'd like to rename my CT potion heal curve table to just CT potion. And then we can use it for any potion effects we have a mana curve. To have a curve in here for any potion effects we want. And I'd like to have a curve in here for mana. I'd like to have a mana curve. And that's going to be your quest. Curve table 10 and use it will change mana. So all we need to do is a new curve. Okay, so we just need to go to this row here for mana curve and it's using the same columns. So something we get 12 38 9 that escalated quick. Quickly. Let's go back to graph view and take a look at the mana curve. And we can scroll out and we can also right click and move around and scroll it to zoom in. Now looking at them from this point of view is nice because we can see sort of irregularities. If we wanted a more smooth curve, we can adjust. I can move this point down by clicking and dragging on it until it's looking a little bit more smooth. We can only drag it. Up or down. We can't go left and right. Like mathematically change them. If we want to go back to the spreadsheet view, go into my gameplay effect potion mana, scroll down to the modifier. And for my scalable float, I'm going to change it from 30 to 1 from it. We're going to use mana curve. And we can use, so now that I'm going to take this one, I do, say 4, and we now have, and 50. Thanks to what goes above, we don't have to worry. Now we know about curve table effects for our scalable floats. And now the word by the curves is a lot better than just the gameplay effects level. Constant value, isn't it? Data-driven, and data-driven values. We'll see you in the next one.